Welcome. My name is Lars Nyborg, and I'm the Director of Production Area of Advance at Chalmers University Technology. Really interesting, I hope, that we today will gather here to see what it means with production in space. Hopefully we have gathered a very interesting program for all of you, and you will enjoy the afternoon here together with us. I have to tell a little bit about Chalmers. Chalmers works in the way that we have a number of departments, but we also have what we call areas of advance and excellence initiatives, where we sort of span across the whole university, and production is one of these areas of advance, and I'm the leader of the whole area of advance in this particular case.
You can try.
Yeah, okay. Then it is, I would like to honor one of my colleagues, Professor Annette Larsson, who came with this idea 2 years ago and said that why don't we launch a real initiative seminar, a workshop for a full day, now it will be half a day because of the circumstances, where we do it on the May 4th. As you know, this is the Star Wars Day. What could be better than organizing a seminar, a workshop with a lot of very interesting contributions on a day like this? So with this, I would like to introduce the moderator of today, who is Assistant Professor Elvire De Beck, and she will then guide you through all these type of activities we have here during an afternoon. So please, Elvire, the floor is yours.
Thank you, Lars. Yes, so as Lars said, I am an assistant professor at the Department of Space, Earth and Environment. I'm an astronomer. That means I study stars, their lives and their deaths, but right here, now, today, I'm not here in that function. I'm here to guide you through this seminar on production in and for space and all the challenges this brings with itself. So, production in space, it sounds quite a bit like science fiction, and maybe it's actually not that much science fiction anymore. We're getting closer and closer every day. I mean, we have entered a new era when it comes to the development of science and technology, that we need to explore space and to eventually, again, land humans on the moon and on Mars, and to develop their bases there. We all know that launching rockets are a big thing for space, right? We need to get our satellites up into space. And these launching rockets are now also being reused, manufactured in a new, exciting way. And we're sending up multitudes of satellites at the same time to build large constellations to support climate studies, communication, weather forecasts, etc., etc. Or just for you to find the way to your next restaurant or home, in this case. As you might also be very well aware of, the big space agencies like NASA and ESA are planning to put humans on the moon soon, in a matter of a few years, and then later we will be going beyond that, being to Mars, which sounds very exciting. And maybe some of you in the audience will actually be among those, who knows, or part of the solution. For these missions, the agencies are, of course, looking at commercial partners nowadays, because they can innovate and really change this space ecosystem very quickly, much quicker than the agencies traditionally would be able to. And this is where research and innovation comes in. This is where people like our researchers come in with their bright new ideas to actually bring us to these next steps. And then we can also take it back down to Earth for a minute, so go away from the Moon and Mars for a second, and think about the fact that we don't only go to space to explore space itself. We also have our technology in space to study the Earth, to study our climate, to know what is changing, how it's changing, what our impact on it is, and how we can mitigate the problems that we're seeing. So we need all of these satellites to actually also be very versatile, very flexible, very smart, very energy and resource efficient. And in one word, that means sustainable. So this is also going to be one of the main focuses of today's initiative seminar. It's how do we do this in a sustainable way? So for all of that to work, we need smart materials, smart technologies, and smart production strategies. So these are all things we will be hearing about throughout the afternoon. So the speakers will highlight the challenges we face when producing for or even in space, because that is then the next step. And they will reveal their innovative ways of tackling these challenges. So maybe they can even inspire some of you to join to tackle these challenges. Or maybe you could pitch in by signing up for ESA's call for astronauts, who knows? Or you might help develop the next generation of instruments for a weather satellite or parts for the next lunar rover. Feel free to browse through all the options. So I want to quickly walk you through the program for today, so you know what is coming your way. There will be three main blocks. First, we will look at the conditions in space. There we'll have two talks, one by Kirsten Knudsen and one by Anna Rathsman, and they will talk about the conditions in space and the challenges for space activities. And in particular, Anna is also going to focus on the space activities in Sweden. Then we will have a slightly longer block after a short break on production for space. So there we will range from looking at the production of satellites, going from producing one satellite to very many satellites, and how we do that in the best way. And for that, we actually have two talks focusing on this from different perspectives. The next two talks in that same block will look at the innovations within the Swedish space industry. And then we will have a third block to close off, and that will be about research and production in space. So there we will look at very innovative ways of having energy storage for satellites, and we will look at how we can be in space, explore space in an Earth-independent way. So for that, we will have two more talks looking at this Earth independence. After that, we will summarize some of today's most interesting topics and give you an outlook of what there might be to come. And we plan to finish by 5. Just so you know, in the audience, you are also requested to be active. All speakers will have 15 minutes to talk, to present their things to you, and then there is time for you to actually also get your questions answered for 5 minutes. So with that, I would like to introduce our first speaker of today, Kirsten Knudsen. Welcome. Yes. So Kirsten is an associate professor in astronomy at Chalmers University of Technology, and her science is on the formation and evolution of galaxies. And today she will talk about how we are all stardust, and how do we know that? Kirsten, please, the floor is yours.
Thank you. Let's see if I can actually navigate in my own slides. There we go. So, our place in the universe is on planet Earth. This is where we live, and this is where we're going to be for quite a while. But when we look up onto space, we have an immense view of the universe. And of course, our view, or rather our understanding of our place in the universe, has changed over time. Looking at the stars, looking in the sky has always played a role for most civilizations, and it will keep doing so for years to come as well, but for many different reasons. But when we look into space, and again, one can start by asking the question, where does Earth end and where does space start? And there's no specific limits, but people often talk about this being maybe about 100 kilometers above our heads. And our knowledge of this has grown hand in hand with the technology that has enabled us to look into space. It has grown together with our understanding of physics, it's grown together with our understanding of chemistry, it's grown together with our understanding of many different things. So technology, together with the willingness of actually transforming knowledge and pushing beyond what we thought was maybe the most obvious explanation, has been the absolute key to understanding space. And with technology, we've been able to actually have travels throughout our own solar system and been able to actually take a few pictures of Earth just looking back. This is one of the famous pictures known as the pale blue dot. And this is part of understanding that Earth, like, even if we might feel Earth is big, space is much larger. The universe is enormous. And just to take an example, within our own solar system, it takes the light from the sun, it's a whole 8 minutes to reach us. To reach out to Neptune, the furthest planet in the solar system, it takes another 4 hours. So this feels like very big distances. But now comes the big step, is that the next star beyond our solar system is just 4 light years away. That, of course, is not something we're going to achieve to reach there in a human timescale. But reaching out is something that we can try to slowly get our way through the solar system, but it's going to take time. Now, the sun is, in our understanding nowadays, is, as our view of the universe has evolved over the past many, many centuries, is that we're part of the Milky Way. The Milky Way is a big galaxy, it's a spiral galaxy. It is so large that we cannot travel out of it. So what I'm showing you here is just an artist's impression of what we think the Milky Way looks like, but it's also a very educated impression because it's based on all the observations we can do of the Milky Way. This is also what we can do of other galaxies. So about 100 years ago, it was actually, we reached to the stage that we could that it was possible to understand that the whole universe was not the Milky Way. There were all these nebulas in the sky where people were wondering whether there were other galaxies or they were just clouds in the Milky Way. And thanks by the combination of understanding stars and understanding and having good technology, it was possible to actually measure the distances to some of these, to the stars in some of these nebula. For example, the Andromeda galaxy, and actually determine that these were actually external galaxies. And thereby, gradually, our understanding has grown over the past century that the Milky Way is one among some 100 billion galaxies in the universe. And that's a good number to keep in mind, together with the fact that within the Milky Way, the sun is one of maybe 200 billion stars in the Milky Way. 200 billion years, 200 billion stars, yes. So the numbers feel very big, and I think we should think about it like the universe is enormous and there is so much to be discovered out there. So it gives us, the universe also gives us a lot of questions and gives us the opportunity to actually search our origins. Now, using our knowledge from the Milky Way and all other galaxies around us, we're able to actually try to establish a picture of the history of the universe. And actually have moved into an understanding that our universe, it's an expanding universe, it has an origin, it has a starting point, which is what we, in the theories, are talking about as the Big Bang. So this is the origin of the universe. And so if we look back, we have the starting point And sometime, some 100 million years after the Big Bang was when the first stars and the first galaxies they started forming. And then moving up until today, at the universe age, about 13.8 billion years, this is where we see where we are today. So in the search of trying to understand where we come from, one of the important things to keep in mind is that the elements from the periodic system or the periodic table that we got from shortly after the Big Bang was just hydrogen and helium and a little bit of lithium. But if we look at ourselves today, we know we're not just made of hydrogen and helium. We're made of basically many different kinds of elements from the periodic table. And so all of what almost all of what we find in the periodic table today comes from processing nucleosynthesis in stars. And that when stars die, they return their matter into interstellar space, into the interstellar medium. And it is out of the interstellar medium we grow new stars. And so this is a recycle, it's a life cycle of the stars and also of the planets that happens here. So if we have, this is just an illustration that shows from the left side, you have sort of the raw material, the gas and the star and the dust, the interstellar gas and dust that will compress and make stars. And out of these stars that are forming there will also be planetary systems forming out of this. Those are stars that live through their life, and their lifetime depends on how massive, how heavy the star is. They will, when they reach towards the end of their life, they will cast away the material again. And so being ready to make new stars out of this, so you get this life cycle. And so of course, we have many big questions out of this. Where do the planets come from? Like, what's the formation of the planets? What's the life cycle of the stars? What happens when they form? What happens when they die? What are galaxies? Why are they made of? What do they look like? Why do they look the way they do today? What is the structure of the universe? What's the origin of the universe? So there's immense questions that we want to understand and answer, seeking answers in. Now, being an astronomer, like one of our, at least for astronomy, one of the primary means of actually getting information from the universe is by looking at light. We have other means as well, but the primary one is looking at light. And the light is, of course, from the full electromagnetic spectrum. And this goes all the way from gamma ray and X-ray, ultraviolet light. The visible light was a very narrow part of the electromagnetic spectrum, but what is what we can see with our eyes. We have the infrared part of the spectrum. We have microwaves, we have radio waves. But also, in order to look at this light, we need to have good telescopes. But we're also living on planet Earth, and planet Earth has this protective atmosphere that's at least protects us and enables us to actually have the life forms we know here. But it also means that there's a certain part of the light doesn't reach us. Gamma rays, X-rays, ultraviolet light doesn't reach us. Big part of the infrared light doesn't reach us. And therefore, in order to actually do observations of space, we need to have telescopes both on the ground and in space. And both places we have a need and are using really like high-level technology in order to be able to actually do these, both, again, the ground-based telescopes and the space telescopes. So on the ground, we have lots of big telescopes, particularly in the visible parts, so up to what we can also see with our own eyes, and a little bit of the infrared part, and then we have from the millimeter and into the radio. I've just put a couple of examples. These are all fairly big telescopes. They're positioned around in different parts of the Earth. And most telescopes tend to be put in isolated areas far away from where we have too much polluting light and too much radio communication. We also have space telescopes. And again, this is just a small sample of what are the many different kinds of telescopes that exist, but ranging from the left side to the right side. It's basically X-ray telescopes, ultraviolet telescopes. There are also a lot of visual optical light telescopes, and that's because, of course, we want to be able to get above the atmosphere in the sense of the atmosphere will blur the light, blur the images, but if above the atmosphere, we can get much sharper images. And of course, we have the infrared and into the microwave. So I want to show just a few different examples of different kinds of such telescopes and what they mean for us for doing observations of space and try to understand what happens in the universe. So and again, I cannot do justice to all the fantastic telescopes out there, but I just want to make a few highlights. I'm going to start in the visual and then gradually make it down the electromagnetic spectrum towards the radio waves. So the first one I want to highlight is the Hubble Space Telescope, and I think many of you will be familiar with this. This is a NASA and ESA mission, and it was launched just about 30 years ago. It has a mirror that's about 2.5 meters big, which for a space telescope is a good size mirror, it's fairly big. But for an Earth-sized instrument, this would be like a moderate-sized telescope. So on the ground, we can build bigger telescopes, but in space, we have to be able to lift from the ground and actually get things into space. Hubble was put in a low Earth orbit in order to enable service missions, and this, of course, is also one of the successes, but why it has its long lifetime. And it's produced immense amount of beautiful images that are available to everybody who wants to use them. And you can just look in the archives. But it's also like the scientific output has been enormous, and again, because this combination of looking at from space above the atmosphere. And I want to show one example, and of course this touches on my own field of research, which is actually looking for distant galaxies and try to understand where the galaxies come from. And if we stare at the sky for a really, really long time, we can collect a lot of light and actually see deeper into space. And one of the examples of this is from the Hubble Extreme Deep Field, where it's a tiny piece of the sky. You can see it on the left side. It's XDF, it's put up next to the moon, just to give an idea of how small that piece is. But you see this beautiful image that has many different galaxies, and there's more than 5,000 galaxies in this image. So it allows us to look really far and look into the early times. Of course, with the quest of actually finding the first stars and the first galaxies. This will not be what Hubble finds, but it's laying the grounds for the next telescopes to do this. Now, we want to take two other telescopes in space, the Herschel Space Observatory and the Planck spacecraft. They were launched together, which is also why I take them together here, and they're two ESA missions. So the Herschel Space Observatory has a mirror of 3.5 meters, and again, that's very big for a space mission. It's an infrared telescope. And the one to the right side is the Planck spacecraft, has a mirror that's a little bit smaller, not fully round, about 1.5 to 2 meters big. It looks in the microwave and infrared. They both operated for about, I think, just about 3 or 4 years. Now, the Planck spacecraft was looking at what we call the cosmic microwave background radiation. This is the first light in the universe. This is the light that came just short of 400,000 years after the Big Bang. So it's basically, through studying this light, I think some of you might know the cosmic microwave background radiation as being sort of the 3 Kelvin light, or the 3 Kelvin background in the universe. And this is everywhere, no matter where we look, we see this. But studying the structure of the cosmic microwave background radiation enables us to see the structure of the universe, and thereby also seeing the structure of the universe structure before we actually got the lights. So how it looked at the Big Bang. So this is a key to actually understanding cosmology. So now we've gone through galaxies, we've gone through cosmology. But the Herschel Space Observatory on the other side is looking at infrared radiation, so it's looking at the cosmic dust. And in the cosmic dust, there's tiny little particles that were actually being radiated, they're being heated, and then we see the heat radiation. So we're basically able to look to the dark side. And so one example here is the Horsehead Nebula, with the right-hand side image being an optical image. We see the dark patches that shapes this, gives this characteristic shape. Looking with the Herschel Space Observatories, we're able to actually see the light from the dust instead. And this is the light that is happening when stars are, the formation of stars, when stars are being born in here. And so this is a part of the life cycle and the cosmic recycle of gas. The last one I want to show shortly is the ALMA, the Atacama Large Millimeter Array. This is on the ground, as you can see. This is in Chile. It's in the Atacama Desert. It's 5 kilometers altitude in order to get high up into the atmosphere. It is 66 antennas that are operating together. And it's working around millimeter wavelength. And it is one of the biggest international collaborations where Europe, North America, and East Asia has gone together to build this enormous facility. And it was also, even from Sweden's side, there is very important contributions, in particular also from Chalmers' side, that contributed some of the receiver equipment with using very novel technology, and also the contribution to what was actually the positioning of all the antennas of all the telescopes together. And it's, of course, this positioning that enables us to get really fine details, because this is radio interferometry, where if you put the telescopes far from each other, you can see finer details and zoom in, and so really zoom in on things. I just want to give a final highlight here of this. This is from a round and young star, it's called HL Tau. And when zooming in around this very young star, that's still sort of basically the formation, you see that there is a disk around it, it's a dust disk. And by looking at this disk and the structure of this, I'm actually able to see the very, very early stages before we reach the formation of the planets. So this is peering into something that is the size a little bit bigger than the solar system. So probably about 120, 150 astronomical units across. So now moving from having gone through various parts of the universe and trying to understand what is in the space and our position in space, I'm going to end here just by showing you an image, which is taken from the Onslaught Space Observatory here in West Sweden. And I would like to remind you that one day, not today because it's cloudy, but on a clear evening, go out and see if you can actually look up at the sky and see the Milky Way. So the Milky Way is the big bright band you see across. But there's also, if you look a little bit to one side, you will actually be able to see the Andromeda Galaxy, which is our nearest, biggest galaxy neighbor. By being at a distance of 2.5 million light years away, it still feels like a galaxy far away. So I will stop here. Thank you.
Thank you, Kirsten. That was a very nice talk. I like your spin on the dark side. While I'm waiting to get in some questions from the audience, I would maybe want to ask you what you would see as the biggest challenge for you or us as observational astronomers in terms of technology development, and then maybe take it to space.
Okay, so there's a lot of different challenges. I'm going to pick two different ones. One is that because people are launching commercially a lot of satellites into space right now, we're actually being blinded, or possibly being a little bit blinded by all the commercialization that's happening to space because of all the communication requirements for communication. So the satellites is a major challenge that's happening for, basically blocking our view. Blocking our view onto the. Well, it's not fully blocking our view, but it's definitely a challenge to how we can see the sky from the Earth. My apologies for that. But one of the other ones is, of course, that we need to have a strong synergy between fundamental research and applied research, because we need to have the synergy between having technology development and the ability and the access to just asking questions as well, and looking for again the basic research, the basic science of actually being ask questions and actually try to explore things, because this is what's always been driving us, is what's sort of beyond the next horizon, what's beyond the next hill. And people don't always go there because they think it is necessarily gives us a concrete thing, but it enables us to actually new discoveries. Like we still don't know, there's the discoveries for dark matter, but we still don't know what it means. But in the future, we will know. So, yes.
Thank you. I don't know if there have been any questions by now coming in. No. Then I think we have time for one more question, and I think I would like to ask you. Now I had a question, now I lost it. I should have gotten one. Are nebulae part of galaxies, or are they found in between them? Is a question from our audience.
Okay, well, that's a very good question. So nebulae are both part of our galaxy and other galaxies, but they are in fact also, some are actually found outside. But a nebula is much smaller than the size of a full galaxy. But indeed, they're actually found. They're not many, but they're found actually. Just like there are many stars found in between galaxies as well. So it's very difficult because they're relatively faint. So if we have to study them, we need big telescopes. So it's a good question.
Thank you to the audience for that question. Thank you, Kirsten, for a very interesting and inspiring talk. And we will switch to our next speaker. So our next speaker for today is Anna Rathsman. Welcome, Anna. She's Director General for the Swedish National Space Agency and also Chair of the ESA Council. She will be talking about what's going on at the agency, and among other things, she'll tell us about micro launches and about the upcoming expansion of S-Range in northern Sweden, but she will also bring it a bit closer to Gothenburg for us. Please, Anna, floor is yours.
Thank you so much, and thank you for inviting me to this event. I really think this is fantastic. Can you see my presentation now? I hope so. You know, when I've been working in space my whole life, you could say. I started building satellites and being a system engineer and project manager, and I really, all my time has really been the big, I think, to see what you can use data from space with, I mean, for the benefit of mankind. And I think that's something that's really have been driving me the whole time. Swedish National Space Agency is the space agency in Sweden, and I think it's fantastic to be the Director General for that agency. And what also very good is that we have the full responsibility, one could say, both for the upstream. I mean, we have the infrastructure, the launchers, the satellites, subsystems, and we have a lot of good industries here, both on the west coast, but also rest of Sweden. But also we are responsible working with with data exploration, trying to really help agencies, companies to be able to use and take benefit of all the data that we got from space. We are a small agency, and that is, of course, we would like to be more people, but of course, it's very easy for us to make decisions and try to do the best for space as we can. And what is also good is that we are also involved in all the different development cycles, both from phase A, beginning studies and things like that, but also helping to take down data for scientists and for another data exploration and use it in a very good way. And we're talking about some advantage for space in Sweden and challenges. And advantage, I think, is that I would say we are very proud of having so many good companies and good scientists in Sweden, even though we are quite a small space nation. So I'm really proud of that. On the challenges that really try to do the best with the one pot of money that we have. Even though it sounds like a lot of money, we should also do a lot with that money. And that's a challenge. One other thing is that we are under the Department of Education. We have a space minister, Matilda Ankrans. I think she's really good, and we have good discussions with the people at the department. But I must say that we have a challenge in Sweden, because if you look to other nations in Europe and around the world, they really have lifted up the space business, or what you call it, to a strategic question in the government. They say, of course, it's good for science and for innovation, like it is in Sweden, but it also covers a lot of other areas, other political areas. And it's of strategic interest for this country, for the benefit for society, for you can talk about Agenda 2030 and all the other things, and commercialization and the positive inventions in the country. And we are lacking that in Sweden. So if I talk about some challenges, is really for us all to try to lift it up on a higher political level. It's not enough to be where we are today, unfortunately, even though they're doing a great job. I would like to talk just a little bit about what we're doing right now in Sweden within space, some highlights. And then we'll talk a little bit about micro launches and also what's ongoing at S-Range. We have a program in Sweden called Innovation Satellites, because we think it's very important to have national programs and also work internationally. So this is a national program with Swedish platform and also Swedish payload. And this is it's planned to be launched during the fall. And actually I have a movie here, I would like to show it, and it's brand new. Unfortunately, it's in Swedish, if you don't understand that, but it's just 2 minutes. I think you can manage that. And it's really fresh, because now it's really at the end of testing. And after that, you will really put it on the side and waiting for the launch. So please show the movie.
väldigt härligt att vara här äntligen liksom, och få se hela satelliten ihop. När man har jobbat med någonting så länge och sett alla detaljer som har kommit samman och nu äntligen så sitter allting ihop och testas.
Vi har så stora frågor om atmosfären, hur olika delar av klimatsystemet hänger ihop. Och då har vi den här lilla satelliten som ska åka runt jorden gång på gång och ge oss svar på alla dessa stora frågor. Det känns helt fantastiskt.
Det är stora utmaningar att bara få ner datan. Man tänker att man lätt kan ta en bild bara på atmosfären. Men vi måste, för att vara säkra på att det vi verkligen ser på bilden är precis det vi tror är, måste vi veta exakt hur kamerorna funkar. Så idag håller vi på att ta bilder på helt vita ytor till exempel. För att se, de blir ju inte då helt vita i kameran utan det är alltid små strukturer och sånt som man måste kartlägga och ha koll på och kunna subtrahera sen.
Mats på sin höga höjd ska ju tala om för oss vad som finns i atmosfären, hur atmosfären rör sig och då måste vi kunna mäta på avstånd. Mäta ljus från alla delar av atmosfären och den information som finns i det ljuset, det ger oss en global bild av det som vi vill veta.
Vi kommer få se då vågor uppe i atmosfären av sådana våglängder som vi inte har kunnat titta på förut. Och dessutom kommer vi få dem i 3 dimensioner. En biolog kanske tycker att det mest spännande är att hitta nya små djur på en annan planet, så är det för oss att hitta de här små vågorna, se de här små vågorna i dimensioner som vi inte har kunnat se tidigare, mycket mindre än vad vi tidigare har kunnat se. Det är ju väldigt spännande för oss.
Det är så många olika pusselbitar som måste komma på plats och passa ihop i slutändan. Man är ju nervös och när man får första livstecken från satelliten i bana och sen förhoppningsvis inser att alla instrument fungerar som de ska. Det blir en jättestor befrielse, men vägen dit blir ju nervös.
So that is Mats. And really let us cross our fingers that everything is going successful during the fall when we launch Mats. And based on the knowledge and competence we have in Sweden with small satellite, cost-efficient satellites and very good cost-efficient payloads, we have been together with other nations created something, a project with an ESA called Arctic Weather Satellite. Here Sweden are PI both for the platform and for the payload. And this is the goal is to make Arctic Weather Satellite service that is going to be used with EUMETSAT. So this ESA project is actually to make a precursor to demonstrate or to show that this system and this concept is working fine. And then hopefully we have this kind of constellation. And this constellation is built on how we do satellites and like Mats in Sweden. And is also a lot cheaper than the other kind of systems that we have had. And also, but still is going to give very good information. So that's a very exciting project. I also would like to mention JUICE. JUICE is going to be launched next September, as far as I know. And it's going to the icy moons over Jupiter. And here we have 2 Swedish PIs for 2 of the experiments, and we are also involvement in a 3rd experiment. So this is also going to be really exciting. As I said, we're also working with data exploration, and it's extremely important that people can use in a good way the data that is coming from all the infrastructure and space systems in space. For example, Copernicus is really delivering a huge amount of very exciting data, but it's not so easy to just use it, what you can call it. So therefore, we have make an initiative together with other entities, what we call a Swedish National Space Data Lab. And there we use an open data source called Open Data Cube, and you put it, like you can say, in different layers. Like in Matrix, we put satellite data and other kind of data that could be of interest and put them together and get a very good information about what is interesting for this agency or this company. And this is totally open. Everyone can use it when we have it in place, everything. So this is really for everyone. And I think for a lot of social benefits, different purposes, you can use this. And one of the examples, we have a lot of pilots ongoing and also finished. And one of them is, for example, to monitoring the shoreline of Lake Vänern. Because now they have chosen to have a very stable level of the water in this lake. And now they can see, okay, how is that, does that influence the vegetation and the fishes and things like that? And can they still survive in a good way when you have like that? So this is just an example of what you can achieve with this kind of tool. If you go to micro launches, I have worked quite a lot with that because before I was employed by SSC and went to Esrange a lot because of trying to really make this happen, that we are going to launch satellites from Sweden. And by that also I was involved in looking at different micro launches. So therefore I believe I have know quite a lot about micro launches. And for me personally, it's quite easy to say that there are room for both micro launches and big launches. The big launches, they can of course offer piggyback launches and also, you know, the price per kilo is extremely cheap. And I also met SpaceX not too long ago, and they said, how could you ever think of something else? We can make it the absolutely cheapest offer that you can get. And that is true, I believe. But on the other hand, you cannot choose the orbit. You cannot choose when to be launched. And also maybe I know there are a lot of other parameters that could be of interest when you launch a satellite. And if you look, here is a picture of Rocket Lab. They're very successful and they have really a lot of customers that are waiting to be launched by them. And you can see they started with 150 kilo approximately that they would like to send up in space. And this is a general trend that they go to bigger launchers, and also they're looking into reusability. For example, if you take Electron, I know that now trying to make some tests to catch the first stage up in space and take it down. I don't know how it goes, but I know it's within their plans. There are initiatives and there are launches from China. There are other ones, a lot of them in US. And if you look in Europe, I think that there are, I would like to mention Orbex is a company in UK. They are not yet ready for launch, but they have a long line of customer, and they are talking about there are 53 parameters that is of importance, and it's not just the price. And in Germany also, there are 3 different companies. It's Rocket Factory, is ICER, and High Impulse. And they all compete of being the first German launchers that is launching satellites. So I think it's really room for both of them, the micro launchers and the other ones, the big ones, different purposes. And if we look at launch sites, here you can see the blue dots. You can see where there now is established launch sites around the world, and it's 8 nations. Among one of them is New Zealand. It's been created when they started to launch with Electron. The orange one is new ones. That is on the way of establishing launch sites. And I think, I mean, if you look for S-range, it's what is big advantage for S-range is that is already in sight. Several of these other places is really they start from nothing. And I think to have the experience since 1972 and before that of launching sounding rockets, even though it's a gap, of course, up to relaunches, is a big advantage. And also that you have a lot of infrastructure in place. One other thing that is very positive both for Andøya and S-range is that the far north, and the air traffic is not so, it's very limited up there. But if you go down and look at for the other launch sites in Europe, it's a quite problem with the air traffic. Maybe not now during this COVID time, but hopefully it's going back to normal times again. And of course, it's a competition, but also collaboration among these launch sites. So let's see how it will develop. If you go to S-range, I really hope that you have had the opportunity to go there. And if not, I hope you will have that. It's quite easy to get there if you compare to other launch sites. You fly to Kiruna and then it's 40 kilometers in car to get there. And it's just to have this big space on land is fantastic. Of course, also for a lot of different tests, but also launches. There are lots of ideas now for making reusable tests for new vehicles, for example. It's a huge area. You can have, they have since a long time been launching more than between 500 and 600 huge balloons and sounding rockets. So, and a lot of very good science have been made here in different ways. But of course, they always would like to develop. And I mean, this work with the sounding launch, with the test, with the sounding rockets and the balloons, they will continue, but they will add other things also. Here you can see the launching sites for the sounding rockets. So the government, as I said, we have very good support of them, and are really grateful for that. They have invested and helped Esrange to invest in 2 test sites, test beds for technical tests for developing engines. And here you can see almost ready the 2 sites that are there in the top of this picture. Down to the left, you can see a restructuring is starting for the launch pads, and to the right is the inauguration of the space ministers for these test beds. And here you can see that you can really see here the test stands in operation. And it's actually 2 competitors. They are really totally separated in the same land. And they work in parallel and make all the tests. And I think they're very satisfied to do that. And they can do it very independently from everything else happening at the Esrange. They're also working a lot now because they also got money from the government for investments in the infrastructure to be able to launch satellites from Esrange. So looking at 3 launch pads, they have integration bays, clean rooms, and also storage for propellant. And I've been there during the fall when we were able to travel there, and it was really impressive what was ongoing up there. So this is the plans from SSC, Swedish Space Corporation, is to have the first launch, if it's going to be commercial or something institutional, I don't know, but they say 2022. When I was working with this, we're talking about 150 kilos, maybe solid. Now they're talking up to 1,000 kilos, and it's liquid engines that is going to be used, and with different inclinations. And they look at also giving different kind of services, like launch service provider of services, or maybe also be just a site for operations. So this is really exciting. And of course, this together with this is very important that we have this ongoing investigation about the space law, because the law that we have in Sweden is really old, but this is really moving forward now. That's very positive. And also that we look into the space situation awareness in Sweden in combination with this launching facility. And that is also ongoing studies that is of importance for Sweden and for the agency. So by that, I would like to end by showing you a very beautiful picture of a launch of a sounding rocket from Esrange. So thank you so much.
Thank you very much, Anna. That was a very nice overview of what we're doing here in Sweden. I got a question. Does the agency work directly towards space colonization in any way?
No, we doesn't, to be honest. I mean, we have a lot of science projects ongoing, but I don't believe they are directly in connection with that. But we are putting quite a lot of money, our total budget, into ESA. And ESA have really big plans of putting people on the moon and being involved in this collaboration with NASA and their plans. So maybe in that way we are supporting that.
Yes. Until I get another question from the audience, I was going to ask, you mentioned that the Swedish Space Agency is a small agency. Does it make it much more versatile than agencies like ESA and NASA? Can we do maybe more innovative things in Sweden because of this?
I hope so. And also I believe so, because, it's very easy for us to gather the whole agency and sit together and discuss something. It's simple, but of course, but sometimes we try to be a little bit careful, because we can change our direction quite quickly within some areas. Mm-hmm. At the same time, we have so limited amount of money, so we have to really be careful to use it in the best way. But of course, we are more versatile when you look at these big organizations. Absolutely.
Thank you. I got another question. with space, there should be freedom to explore. How much do you think the budget available is affecting the development process? And do you think SpaceX is blooming because of its private status?
It's a good question. I think, for sure, if we had some more budget putting into science and new project, we could do much more. So what is positive in Sweden is that we have a lot of good scientists, very good ideas, and when we got our applications, the level of them is really high. So we could do much more. The problem is that we need more money to do it. But if you look at SpaceX, I think it's what they dare to do is they dare to take risks. They say that, but they have, as you, or I think all of you are aware of, I think they failed 12 or 13 times before they were able to really land the first stage on ground, and they still say, oh, it's almost successful. We can never do that in Europe or ESA, never. So I think it's the willingness to take risk is extremely important, and SpaceX is really, really impressive what they're doing, but we should keep in mind they also have a lot of institutional money from NASA. Otherwise, they haven't succeeded. So they had another kind of system.
Is this maybe also a call for more risk capital to be put into Swedish and European space development?
Yes, I think if you could combine money from taxpayers' money with risk money, it would be very, very good. I think we could do a lot more.
Then I got a last question. You mentioned that it is not possible to choose orbit when launching with a big rocket. Why is that?
You have to take to go with this big platform where you put a lot of satellites on it, and they have a specific orbit, and then they poof you out, take you off this, and then you have to use that orbit that you got there. Of course, then if you can do something by yourself, your own satellite, you can move away or something. But otherwise, you have to have that orbit that you are the main rocket have.
Okay, thank you very much, Anna, for a very interesting talk and a very nice question and answer session. So with that, we conclude this first session for today, and we will have a short break. I will be able to put this up, yes. And we will, yes, exactly. We will start again at 2. So we'll have a short break, and then we will take you back to space again. See you soon. Hello and welcome back to Production in Space. For the next hour and 20 minutes we will turn to the production of materials, components and satellites for space. We will have 4 talks in this block, each focusing on different aspects, from mass production of satellites, which will be our first talk, over the flow of production, to space activities and innovation that are going on across Sweden. So for the first talk, we actually have 3 speakers. I see that Ola has also joined us virtually. So we have 3 speakers: Ola Isaksson, on Zoom here, who is professor in product development at Chalmers University of Technology. And here on stage, I have Olivia Borge and Massimo Panarotto. Olivia is a PhD student in product development, and Massimo is associate professor, also in product development. So the 3 of them will join together and talk about how satellites are developed today and what the challenges might be for satellite production in the future. Their talk is titled "From the Design for a One-Off Satellite to the Design for Mass Production Satellites. Do Priorities Change?" Please.
Thank you very much. Let's see. So it's a very kind introduction. I just can't see my own slides, but that's coming, I guess. Let's see. So, yes. So, thank you very much. We have just so small. Just a minute. Yes, I think we will talk about lots of challenges that perhaps are interesting when we want to explore or make use of our endeavors in space. And first, I'd like to draw your attention that everything that we want to do in space requires some type of product to realize that. And of course, as we want to do other things that we do today, we also need to create new types of products, and we also will require new ways of producing these products. So that's what we're going to reflect upon today. And together with my colleagues, Olivia and Massimo, are on site. So we can take the next slide. If we just take a simple look on the satellite, on the process of getting a satellite into space, operating it and using it, and taking on our engineering glasses, we quite quickly recognize that we need some kind of rocket, and the launch process itself is quite extreme. There are quite a lot of loads and thermal constraints and dynamics going on that both the satellite and the rocket itself needs to sustain. And lifting mass is very critical, why mass needs to be kept low. So there are highly optimized products that must not fail as well. Once we get into space, we also need to get the satellite into position, which requires movements. We also, during its operation, for many, many years, typically if you're in orbit, you also need to navigate and move around, perhaps move from debris that exists in space nowadays. And we also need activities for putting the satellite out of production, out of order as well in the end. All of these conditions require quite different techniques and different functionalities of the products with robustness, dealing with these loads. So let's turn into production for a second and see how do we then integrate and make use of new technologies for doing that, new production technologies. In our research group, we look into integrating new technologies into complex products, and we do it in many different contexts, but today we talk about 2 of them actually. One from a European project called CHEOPS, where we look into the next generation Hall thrusters for satellites, but we also give a glimpse into some of the rocket technologies that also benefit from space applications. So now, Olivia, take the next slide. What is really the view of manufacturers of space equipment today? Do they benefit from new advancements in manufacturing technology, for instance? Do you have such examples?
Well, yes, as you mentioned, products for space applications, they need to be able to withstand the harsh environment from space. And because our ability to repair and to service them is quite limited, we have to design and we have to manufacture them to have a very high quality. And then at the same time, to launch products into space, we need to use launch services, which are very expensive, and to reduce cost. What we want is to reduce the weight of our space products. And well, at the same time, all of these products with reduced weight need to be robust enough to be able to withstand the load conditions during launch. So in the end, we have a product that has to have a very high quality and very high performance, but at the same time be very lightweight and robust. And all of these technologies make space products to be extremely expensive and with very long development and qualification times. And it is here actually that new technologies come in, because implementing new technologies, what companies aim at doing is to reduce cost and development times, while hopefully maintaining performance or even increasing it and maintaining and increasing quality. One of the examples that we have right now is additive manufacturing, which is a technology that is increasingly popular in the space sector, basically because of the nature of this technology, because we can manufacture shapes that are quite complex and that can help us to increase performance. And because of the versatility of this technology, we can manufacture a wide variety of products. We can go from very large products for launchers to rather small and delicate products for satellite applications. And we have a couple of examples here from the companies that we usually work with. We see at the bottom of the slide, for instance, we see a turbine manifold from GKN that has been 3D printed. This turbine is for the Prometheus rocket, about which Marcus from GKN will tell you more about in later talks. But what is particular about this turbine is that it's completely integrated. It is manufactured as one piece. Then we also see the example of RUAG's antennas that are also integrated and that are a very good example of additive manufacturing capabilities of producing something with very tight tolerances and very specific surface requirements. And then to the right of the antennas, we see OHB's flow connectors that are used for, they are miniaturized flow connectors for fluid management systems that are going to be used on board of satellites. And what we can say is that all of these different examples come from extremely different products, but in the end of the day, what they have in common is that they all need to be redesigned for this new technology. Because we cannot just swap technologies when we want to innovate. We have to redesign products to optimize them for the new technology, and we also have to redesign the whole product development process.
Okay, thank you very much, Olivia. We will now take another view on this and continue to challenge the manufacturers. We've learned about the new types of businesses coming up in space and new services. Does it really impact manufacturers, and how they think? Do they have new priorities when producing satellites? Please, Massimo.
Yes, thank you, Ulla. So, traditionally, satellites have been mainly used for scientific missions. And here I have an example from Bepi Colombo, which is a satellite that is actually on its way to Mercury to perform some scientific tasks. And we can see that these satellites are very large, more than 4,000 kilos, and they are very large in dimensions then. But then we have new businesses coming up for space. And then I will show you how this is impacting the way that we engineers, we have to design and to produce these satellites. As first example, I take satellite mega constellations. So there are some companies now, private companies, before it was mentioned SpaceX with Starlink, and this one is actually OneWeb, which is it's actually a competitor of SpaceX. So these companies, they have the business objective of covering the Earth with many, many satellites to give internet connection to the entire Earth. And as you can see here, the satellites are much, much smaller than than a typical satellite for science missions today. We can see that it's less than 1/10 of a satellite today. And there are many, many more satellites. Then apart from these businesses, there is also a big explosion and a big trend of what is called CubeSat that we have here, a little 3D printed example. But these CubeSats are basically very tiny satellites. You can see 1.5 kilos. And basically they are built by universities and launched for education purposes. And we can see that today we have more than 1,000 of these tiny satellites already orbiting around the Earth today. So, how does this impact production, moving from the business that you can see on the left, moving to the businesses that you can see on the right? Well, here I'm taking a production facility of a satellite today. As you can see, this is a very large satellite. It is very individualized and very customized for that specific scientific mission that it's going to perform. And it takes a lot of time to build, so typically from 12 to 18 months. And as you can see from this picture, you can see that the people that are building this satellite are actually moving around the satellite to build the different parts. So if we want to make a parallel to what we have on Earth, this is very typical to the design of a ship or a yacht. So we have this design and production of a very individualized, customized, very expensive, individual, single, one-off product. Now when we are changing this business and we are going towards higher production volumes, such as OneWeb, here I'm taking the picture from actually the OneWeb factory in Florida, where they are targeting the production of 2 satellites per day instead of a satellite per year, and 900 satellites targeted. You can see that the production facility, even visually, resembles very well what is a production line of a car today. So even visually, you can perceive that there is some change going on when it comes to production. But then for us designers, for us engineers, what does this mean? So now I'm picturing basically this graph where I'm picturing the cost of the satellite against the production volumes per year. When we are in traditional businesses with very low production volume and very high cost, here we basically, engineers, we can compromise the unit cost of the product in favor of performances. This means that we can almost accept that the product can be a bit more expensive as long as it is very performant for the science mission that is going to perform. Because often we have also governmental programs behind, such as ESA. When we are moving instead to higher production volumes, such as OneWeb, actually the trade-off is flipped around. So actually we can compromise performances in favor of unit cost reduction. So actually we can accept that the product will perform a bit worse, but that actually the costs are kept very low. And this is because the performance is given by the constellation as a whole and not by the individual satellite alone. But then what is interesting is that we have another effect. That there are some other aspects of the design that are coming to play a bigger role than what is a traditional business today. And these aspects are, for example, the flexibility of the satellite, the manufacturability of the satellite, because we are producing so many, and also the development and testing ability of this satellite and the development effort of it. So and this comes as a challenge for us engineers. So while these aspects are very much more important for these new businesses, they are much more difficult for us to judge and quantify in the early design stages compared to, for example, performances and cost that we can calculate. So, and for this I'm giving some example that is taken from one of our projects. and it is related to our electric propulsion system for satellites. This is basically an engine for a satellite that is taking a propellant, which is typically a gas, xenon, and is used to perform thrust to the satellite. So while xenon is very good today, is likely to going to be very expensive in the future, especially if using so many satellites. So actually today customers are interested in making these systems flexible and compatible for other types of propellant, such as krypton. However, this involves a number of trade-offs. And here I show some of these trade-offs. For example, we could have option number 2 here, in which we try to make this system very flexible for using both xenon and krypton. But we have the downside of it that we have actually to develop 2 systems instead of 1. So actually the development effort is going to double. So this is probably not such a good option. Or we can actually make other 2 designs in which we actually try to make a smart design for which we can only change the type of propellant without changing the system. And this has the benefit of giving us flexibility with a lower development effort. But at the same time, it could be that this system is very sub-optimized because it's using components that need to be compatible with both types of propellants. So probably then the performances and maybe the reliability of the system is going to decrease. So basically we have this trade-off between the development effort, the flexibility, the performances of the system, and the reliability. So how do we go to solve these trade-offs? Well, now we'll talk for 1 minute about what we do in our research group. So in our research group, we are comparing different types of designs, probably 100 of designs, such as the 4 that I've shown before, along a number of dimensions. And you can see in the chart below here that each of the lines in this parallel chart, it's basically a different design, such as the 4 that I've shown before. And these are performing differently in different type of aspects, such as the unit cost, the reliability. Then we can make a comparison between these alternatives, and then we can actually take the most promising designs and to see what is their effect on actually economic models, so we can see their cost and revenue profile a long time. And here I will show briefly just 2 examples of what we can do. For example, here I show option number 1 and option number 3. And you can see that the option number 1 in blue, although it has higher unit cost, it is actually performing better in terms of cost and revenue because of its higher reliability. This is because if we have our one-off satellite, we cannot actually accept to lose the satellite emission. Instead, another type of trade-off that we can make, and this is made for constellation, is that we can make the same trade-offs between unit cost and reliability, but at the same time we can quantify and see the impact of other aspects, such as the development effort. We can see that here the option 2 in blue has a higher development effort than the option 1 in red. And this is making that the lead time for developing this satellite is much longer. So this in the longer term is going to have a longer payoff period compared to the other one. But also we can make a new trade-off of a new design, that is this option number 3, in which actually it has higher flexibility than the other 2 alternatives. So this means that these alternatives actually has higher value compared to the other 2 options because we can easily change the propellant if the krypton option or the xenon option could be more favorable in the future. So to conclude, what we can remember from this speech is that to be successful in the new business scenarios, the manufacturer of space products need to prioritize and investigate new alternative products and production alternatives already since the early design. And we from our research group are supporting these types of trade-offs.
Okay, thank you very much, Massimo. We also know that humans have always been fascinated about space and what to do in the future and what we may do. It's been mind-provoking many times. But do we have any aspects of production also for the future in space? Back to Olivia.
Yes, actually, we can say that this trend for cost and development times reduction is going to continue. And we will see a shift from manufacturing on Earth for space into manufacturing directly in space. Because in doing so, we can say that we get rid of the very harsh robustness requirements that we need to withstand the load conditions during launch. And then if we look even further into the future, we find all of these initiatives proposed by the different space agencies in the world about, for instance, establishing moon camps or sending astronauts to Mars. And in those situations, it's going to be extremely useful to be able to gather resources and use those resources for insight to repair existing space components or even redesign and manufacture whole new components. And if we think about even further, we find absolutely autonomous and intelligent products that are able to gather resources and self-repair or even self-manufacture. But what we can be sure about right now is that in order to settle into other planets, in order to foster human exploration, we need to be able to manufacture in space. But in order to manufacture in space, we have to first be able to master manufacturing on Earth for space.
Yeah, thank you. And I think this is, with the next slide, it's our conclusion as well, that we do see a future for production in space. We see that we need new types of products to accomplish what we want to do. And we also stress that we really need to design these products to make use of the forthcoming production techniques as well. Thank you very much.
Thank you, Ola, Olivia, and Massimo. I see that we're running a bit late, but I will have one short question for you, although I don't know how easy it will be to answer. How is 4D printing concerning space applications being looked at by your research group? And is there some current research on this that you could share? I don't know what 4D printing would be.
I think it might refer to 3D printing of materials that can change over time due to environmental conditions.
Okay.
For instance, due to humidity, the shapes and geometries can change once you have already printed them. At our research group, we don't work with that, but I know that research is ongoing for those type of structures in general, and of course also for space.
Okay, thank you. With that, we will thank our three speakers and go to our next speaker. So for this next talk, I can welcome someone who claims to have first-hand experience as a satellite because he's 2 meters and 2 centimeters tall. However, for today, we will focus on some of his other achievements. And for that, I welcome Björn Johansson, who is a professor in sustainable production here at Chalmers University of Technology. And he will be focusing on the challenges that, for example, companies like RUAG have to face when increasing their, as was already mentioned by the previous speakers. So please, Björn, go ahead.
Thank you very much for the introduction. And also thank you for previous speakers. They actually already introduced a bit of the talk I will have today as well. So I will try to take a little bit perspective on environmental part for space manufacturing and production systems for space industry. As you might know that recent days now we have seen that the glaciers are melting even faster, 30% faster than a few years ago. And that could be really disastrous in the end. And we also know that greenhouse gases increasing and so on. And all of this information is very much because of satellites and the pictures they take and the connectivity they give to the globe to spread the knowledge and get more awareness. So my message would be like, awareness is the key to actually do something, and we need facts to base our decisions on, and satellites and the space is giving us a lot of that. As you also might have heard, that Sweden will become climate neutral 2050. We signed a European Parliament agreement just a couple of weeks ago. And this picture you see here is depicting the GDP on the blue line, which is continuously more or less increasing. And the emissions is actually decoupled nowadays. So the CO2 emissions from Sweden, Swedish society is decreasing, even though GDP is increasing. And that's quite unique in terms of countries worldwide. And I think that's a really good idea, and the knowledge and the innovations that we have in Sweden is definitely worthwhile to distribute to the rest of the world as well. And not only Sweden has been signing this deal, also Joe Biden had a talk also a couple of weeks ago and agreed to follow this, and many other countries as well. So I think net zero emissions by 2050 is a really good target. But to reach there, I definitely think we need satellites, we need the communication, we need many different things, navigation, broadcasting, logistics, and the science that we work on. And also for weather forecasting and understanding what's happening with our globe, so we can actually take the right actions. So I think this is a really good initiative with OneWeb, for example. And I think also that digitalization is the key to reach this sustainable globe in the end. Without information and knowledge and sharing what we know and how to act to make it more sustainable, that's one of the key factors that we need to think about. We already had a small introduction about OneWeb. This is one of the reasons why Ryvag needs to increase the production, and also many companies like GKN and other companies that work to build satellites and parts for rockets and so on. In Ryvag, they have a big mission to keep 100% quality on their products. So for sure, you don't want to send up something in space and it's going to fail after a while. You need to make sure it actually works perfect and it's no failures going on. And when it comes to production in this case, actually the production mechanism is not the physical production that takes the longest time in the factories. It's much more about testing, like testing in vacuum or in extreme conditions with shaking the product and putting it into heat and other things. And for this, Ryvag needs to change the production process a little bit, because they are doing interesting parts like antennas and computers. This is one of the computers. They make a couple of hundreds of those, and it's only 2.3 kilos onboard computer, but it's actually the brain of the rocket, so it's a really important component. And of course, all components are important in a rocket because you cannot change or do anything once you have launched it. So we have been working with Ryvag now for some years on this OneWeb project and other parts that will increase the production. And the increased demand of components nowadays is a lot because of the OneWeb and other constellations with many hundreds of satellites is going to be orbiting the globe to give us connectivity and information about what's happening on the globe and also outside. So in Ryvag's case, they are looking at a 400% increase of production. And within the facilities right now, the focus has been, as I said before, on quality as the main part of the core business idea. But to make 400% more with the same quality, there's a lot of changes needed to be done, like Massimo was talking about before. If you make a one-off product, you have more like a project-based approach. But if you make many hundreds of products, you need to have a more flow-oriented manufacturing approach. So we have been working with the layout planning of the factory and looking at the flow orientation, looking at digitalization of the order handling. Instead of having paperwork moving around in folders, we now are introducing it more online, and you can see it in digital version in a computer anywhere at the company. We also worked a lot with the social environment for the workers. It's quite stressful not to know what you are going to do next. You rather need some support online as well, then, so you can see on the screen, this is the next product I will do, are the steps I'm going to assemble, or this is the test I'm going to perform. So giving the operator a lot of support to understand what's going on in the factory and keep them more aware of what's happening and calm and better work environment in that way. RUAG is also working with an engineer-to-order principle, so it also means that the orders can change a lot. When they come in, one order, it can be changed within a few minutes or before you actually start production. And once you have printed on paper, it's not easy to change it, but if you have it digital, it will be much easier to implement the change without disturbing the actual work going on. So when we look at this picture, most of you have probably seen the Industrial Revolution parts before, the steam engine in the 1800s and so on. And we are now on the 4.0 Industrial Revolution with a lot of digitalization and automation of data. This is going to help the space manufacturers a lot. For sure, in space is already a lot of digital solutions, of course, because there's no cables available to connect to the satellites and other things. But on the ground, we also need to implement this. It has been more simple production mechanism before. It also has to be more advanced now to take care of increased demand with good quality and with good social aspects without actually ruining our globe in terms of resource extraction and waste. And already now we can also see that the European Commission is launching Industry 5.0. And this is also quite interesting to see what's going on here. It's more human-centric, so putting the power to the people, and also something that might trump sustainable in the end, to be a even higher view on sustainability is to look at resilience, so we can be flexible and adapt technologies and be more adaptable to changes. For example, now with COVID, we were not really resilient enough to maintain it, but we are quite quick to develop different antidotes or virus, what's it called? When you get some flu shot or something for that, to remove the virus, to get antibodies for the virus. All right, when we look at RUAG's previous forecast and planning, they had long-term planning every 3rd month, and then looked at the project manager and see what's coming in. But as I said before, the change can come really short, with short notice. So they also need to have weekly planning meetings and what is going to be done this week. They introduced lean manufacturing quite a long time ago, and they have whiteboards in the factory for operators to look at to understand what's happening right now on the MDI boards, for example, for short-term planning. But all of those then, if they are digitalized instead of on the whiteboards out in the factory, managers can change the production sequence and be more flexible and more resilient to changes in the order handling. Also, when we started off with doing a screening of the actual production at RUAG, and this might look a bit strange, but this is the production flow of different products in the factory. So it's a top view of a factory. It more looks like a spaghetti or maybe a noodle soup or something. A lot of lines all over the place, a lot of movements of the product. So in order to make this for mass production, we really need to straighten out the lines to make it smooth and straightforward instead of going back and forth all over. So more flow-based instead of product-based. So how can we then implement a structure to go from the low volume that is was right now to the higher volume with 400% increase? And then we can also foresee that the volume will be flexible over time for the future. Once they have created, for example, OneWeb, it will take some years before we need to do any effort again to change or do something new. So the volume could be flexible for the future as well. So we have to also adapt the factory to be able to take a low volume without hitting a big loss for the companies. So in order to address these challenges, we did value stream mapping and pinpointed different parts of the flow which were critical to understand where are the bottlenecks and where are the critical factors in a flow which will limit the output of the factory. And we did this is just a small part of it, but this is more straight lines, as you see. All of those actions would be in different rooms moving around in the factory, so it will be more straightforward if you could build a factory like this. We also tested this implementation in simulation models with more visual understanding, so operators and personnel and managers can understand what is happening and who is doing what. And we even took it one step further to do a 3D scanning of the factories and parts of it to make operators be able to visualize themselves when they walk around and do operations in the factory. And here it's really near to real environments, as you see on the video. So with this understanding and this knowledge now to see that the factory is not really flow-oriented, RUAG has decided to rebuild the whole factory. They started just last month and they will be done with it already in end of summer during fall. And that's quite a quick rebuild, so it will be a big effort for them now to change the production flow, enable to increase the production rate with 400%. For the work done then, so we looked at understanding of the current factory, data collection, flow description, etc. We made some technological development and personnel preparation by discussing with them, talking with them, what kind of aids do they need, how would they like to have it presented in the computer screen, so we can have more data-driven decisions and new software and methods. And then the factory reconstruction has started right now, and the implementation of the solutions that we have is on demonstration activities right now, so I cannot really show you, but it's ongoing. And for RUAG, it means that the change process is ongoing, and we have done a lot of implementation of the research done to reduce the waste in the factory, to have a better work environment, to increase the economical value in terms of revenue and also in the mass production concept, while also maintaining 100% quality, of course, because that is the key thing that they need to do. And that's for all of the companies that send things into space. For society, we have different graduations for PhD and licentiate and several master student projects, publications and presentations. And also we have distributed this to other companies. We have talked with GKN and with Volvo, with SEVT, with Saab and other companies as well, so they can take use of the information and the research we have done. But all in all, the most important thing I would like to see with this, and I think about it as well, it's that we are enabling a digital solution to gather knowledge and facts to make a better society and a more global, sustainable world to live in. And also it's a bit hard only to implement things to change one thing. So I think we need to get awareness first, to understand what's going on and get facts in, and that's what the satellites and space can help a lot. With all the previous talk that we saw with the connection to UN sustainability goals, for example, from Anna earlier. And then when we know what's happening, we can take the right action. But we also have to keep in mind that we as people have to do the decision. We are sitting on the knowledge, we are the decision makers and the managers of the companies as well. So it's definitely worthwhile to choose the right part of the scale here. Would you like to save our planet, or would we like to earn more money, or would we like to make a better living environment for the people and society? So we have to be careful with this, not only to optimize on economical goals. We have to think about the environment first, otherwise we have no society, and if we have no society, we have no economy either, because they are all part of each other. Thank you very much for your attention. Looking forward to questions and the coming speakers as well.
Thank you, Björn. That was a very nice summarizing message, I think. I am waiting for questions to come in. In the meantime, I will ask a question myself. So you optimize the production flow at the RUAG factory with OneWeb in mind, basically. Did you manage to learn much from other industries that needed to increase their production flows, or is this really something that is unique to the space industry right now?
I would say every industry is unique. I've been working with over 100 companies around the world with different factory reorganizations or new factories as well. So it's always new settings, always new prerequisites. But I would say for space industry, the 100% quality is probably the highest challenge, especially when you go for mass production. We had one discussion with the RUAG management once to say that we would like to reduce the quality to 97% to speed up the production flow. And in that meeting, people are just screaming in the end because that's not an option for them. But we didn't mean to send up the failed versions, rather produce it faster and then doing all the tests and only accept the ones that are in good quality after. So it's more the production concept does not need to be 100%. But of course, when you send it up, it has to be 100.
No. Let me see if I got any questions. For now, not. I have another question. Do you think that the digitalization will cause the radical changes that might solve big problems in the future, or will the radical changes more lie in the production itself?
I think to do a radical change, as I said in the talk as well, we need the facts and information, and I think digitalization is the means. It's more like a conveying part of the messages to get the right information in front of decision makers to do the right choice. So I don't think radical change come from digitalization per se, but it will enable a lot of radical changes.
And then I have one last question here that I got from the audience. What role does Chalmers actually have in the reorganization of RUAG's factory?
We are an external part, of course. We don't have any personal, not any Chalmers interest inside of RUAG, but we have several people working together with them in different projects. But of course, when you get funding from the Commission or from national agencies, we need to also distribute the knowledge to other companies. So some parts we work together with RUAG and we maintain the information at their site. But in the general term, when it comes to how to optimize the flow and how to digitalize the production information, that we are sharing a lot of that research with others as well.
Okay, thank you very much, Björn.
Thank you.
We will be going to our next talk if our speaker managed to dial in. Since 2015, she has been active in an organization called Innovation and Growth for Space, or Rymd för innovation och tillväxt in Swedish. This is a regional space innovation project run from the Swedish space town of Kiruna, together with the Graduate School of Space Technology. And she calls herself a rookie in the space industry, but I don't think we should believe that. And during her talk today, Anna will talk about the emerging space business in northern Sweden, but actually also across Sweden as a whole. And her talk is titled "The Light Comes from the North" on the emerging Swedish space industry. Please, Anna, the floor is yours.
Thank you so much, and I hope you can hear me now.
Yes.
So you see my background. I'm actually up in Riksgränsen, so just by the border to Norway. So I think this is a good spot to be for giving this talk. I just hope I won't be that disturbed by skiers coming in here after a day in the sunny snow up here, about 2.5 meters of snow, I think, still. So this is my team. So we're attacking additive manufacturing. We're actually working together with Ola's team as well. And some of the speakers that have been talking previously have already touched upon what I'm going to talk about, so I'm going to be quite quick. Seriously, this is my team, and we work in the Graduate School of Space Technology, and we work with this program Read Space, where we have conducted several technology projects. But I also work more broadly, and we have recently got involved in European universities with a space university called Universi, that I think you will hear more about. And Peter Turlin from my group is active in developing that program. And we're also actually applying now a new PhD student in space debris. The Graduate School of Space Technology was actually national starting in 2001. It has so far graduated many PhD students, and I wanted to bring some of them with me here. So I will share a film clip, and I hope this will work. It's via YouTube. Please.
When I was young, there was no space education available in Sweden. So every time I come here, it feels like a dream. Back then in 2001, there was a need from Swedish industry to get more research in space technology and to get more specialists. And the aim was also to strengthen the education, especially in Kiruna. The best thing about my job is to see the energy and the ambition among the PhD students. There's always something exciting going on, from ground level all the way to outer space. Being the coordinator of the graduate school, I must say I'm very proud. Since the start, 40 PhDs have graduated and many more are on their way. And they are working in industry, academy, or they've started their own company, both in Sweden and internationally. The school has not only given them a chance to get in contact with so much space research and so many space actors, they've also got a network where they can strengthen and help each other with different questions. If you also have a dream about space, don't hesitate to join the Graduate School of Space Technology. Here you will have all the opportunities to fulfill that dream. You are very, very welcome.
So back to the presentation then, and when we say you're warmly welcome, now many of those you saw at this movie, they have graduated, so we have new places for you, and we are again applying for the graduate school to become national. We already have an agreement also with Chalmers and Ola's group. Why the north of Sweden then? Well, we already heard Anna Rathsman, so I'll go rapidly through this. But as you see, the traffic from flight is quite limited up here, and we have the history from the IRF since the 50s. And this region then provides this very special conditions and this huge roadless land, which allows us to have this space center. And showing a few more pictures of S-range. I would just like, I couldn't spare this picture of the first launch that we had actually close to where I come from, Harads. So from Kronogård, it was sent in 1961 already, the Pelutnik. So this gives us a path dependence in Sweden that gives us excellent opportunities if we look from the history and into the future, and especially the investments that are done at S-range lately. And this is really needed because the Swedish space industry is quite limited. As you can see, only around 1,500 people are working in it. And even though they are very high tech, it's still very few. And the global space industry is growing tremendously, and you see Sweden with 3 to 4 billion per year if we merge all the companies, while the global turnover is estimated to grow rapidly from, well, you see, so we're like 1,000 of the global market, and with our legacy we should be able to have a really nice growth. And that is actually what is happening. So what we've been doing in this regional project, we have involved many from all over Sweden. We have worked together with ESA as well. So we have developed this ecosystem, or rather articulated it because it is already there. So we're working with many academic partners, with authorities, but then the most important thing, the business, and that it's also both the regional SMEs and startups in the space industry. And several cluster programs and the similar that we're involved in that helps bringing more out of this business. So the R&D projects that we just saw, the innovation activities that makes this actually a vibrant entrepreneurial area, it gives very good possibilities to create more businesses. So involving students, PhD students, and also to attract SMEs. And then we have the ESA Business Incubator that is also situated both at several places in Sweden. And the testbed space that we're developing, both at Space Campus, where we're employing quite heavily right now, both senior researchers and PhDs, and working together then with many companies. And especially I would like to mention again, as Anna told us, about the new S-range and the test bed and small sat opportunities that are being opening up there, while Kiruna the town is also moving, as you know, due to the mine activities that also give new opportunities. And this actually, we have seen, attract new companies coming from all over the world to develop their business in Sweden, to try both their rocket propulsion, to further develop their manufacturing, as we heard here, more developing as we develop cars, the production of space equipment. And I just gave an example from a pork shop story that they are usually young, and they usually have what Björn told about, the Save the Planet dimension of why they are doing this. We also recently got two of these innovators were awarded at the Innovation Riksdag in Sweden last week. The Center of Excellence that we are building at LTU, well, we thought maybe would be more of a regional history, but we see that we would like to, and we have to involve several universities. So we would really like to collaborate with all of you over Sweden, but of course also internationally. And we see that cross-fertilization is so important across different topics and different research subject areas. The aerospace cluster, I would like to finish with that. So this is the cluster for companies, both the big ones, but here we're also opening up for a larger proportion of SME in the total turnover of Swedish aerospace. So these are some of the participating companies, the member companies. And we have put in a corner here, we are also running business development programs specifically for developing space business. So that is something that we are experimenting with now and that we would like to continue with. And this picture shows that space with its, well, 1.5–2 billion Swedish kronor is just a small part of the Swedish aerospace business. So let's together increase the opportunities of this to grow with the resources we have and the synergies that we can get out of developing our ecosystem for space. So with this, I would just like to say welcome to join us. And I look at my watch and I actually see that I have time to play this small video just to welcome you to work together with us. So with that, I say thank you and warm welcome to contact any of us. So I brought a few friends with me there also on the contact page. And thank you so much for organizing this day.
Thank you, Anna, for a very interesting talk. I agree. First of all, I want to just say that I agree that tackling space should be a national endeavor. I mean, we are a small country. If we fight for our own cause, it's going to make it harder. We should definitely get together. So I'm very happy to hear that the graduate school will again be a national graduate school, hopefully. I will check if we got any questions here. I have not received anything so far. So I was wondering if you could tell us what the best or what kind of lessons you've learned from setting up a regional network like RIT.
Well, the lesson is actually that one, that we can't have it regional. we can offer what we have in our region and then invite all of you. So we have had these space innovation forums. We have had 12 so far, and we have had guests coming from all over the world actually. But that we actually see the space business as a Swedish national thing to develop, and that we have so much potential to develop it further. But I mean, we worked together with GKN very much, for example. I used to joke that when I started to work in Luleå, I have never been so many times to Trollhättan as when I started to work in Luleå, for example. So it's a little bit difficult with the EU money that are regional, because then we have to do activities that bear their cost in that specific region. So I think that more flexibility in the European regional funds is good, but that have been quite okay. They have been quite flexible.
So I'll take this as a call for broad national collaborations when it comes to space. Space is becoming more and more important for all kinds of actors. I mean, people might not be aware of this, but there are many commercial players that are coming in now with a need for a space connection, which they beforehand maybe didn't see yet. So this is really opening up many doors, I think.
Yeah, that's really what another experience that we have seen. That was maybe a little bit idealistic from our side to involve traditional like manufacturing companies that has no connection at all to space, but many of them came to our space innovation forums, and then now they take part of our business development programs for space. So that's really great.
That's very nice to hear. I think with this, I will conclude for this block. I thank you again, Anna.
Thank you so much for having me here. Thank you.
So after a short break, a bit longer than the previous break. Wait, my slides are not coming up here. Yes. Oops. Okay. We will have a break now until 15:40, so we'll have a 20-minute break so everyone can regain their energy for a last trip where we will take you also to the moon and to Mars. So get ready. See you soon. Welcome back, everyone, after hopefully a nice break. For the third block of today, we will stay in space and we will start exploring research and production in space. So we're going to slightly, well, or even more exotic things. We have 3 talks scheduled for this block, and after that, Lars and I will hopefully be able to land you safely back on Earth to have some post-discussions. For the first talk, the first talk will focus on some groundbreaking ways of storing energy, which is very much a change that is needed for sustainable space exploration. So this is yet another big puzzle to solve. And to hear something about these new radical changes, we have Leif Asp to talk to us. He is professor in lightweight composite materials and structures here at Chalmers University of Technology. Leif will talk about a multifunctional material that can simultaneously carry mechanical loads and store electrical energy. And this is then the key to providing massless energy storage in satellites. Please, Leif, the floor is yours.
Thank you so much. And thank you for inviting me to this fabulous event. It's been very nice to listen in all day. So I will talk about my stuff then. And that's, as you said, lightweight composite materials. And the idea is to build in functions in the material to allow for energy storage without no extra cost in weight or perhaps volume. So it's illustrated here, the structured battery composite material, which is a material with intrinsic ability to take and carry mechanical loads and to store electrical energy as a battery. And we have ideas then to provide these for use in satellites, for instance, and in automobiles and laptop covers and so on. And this was illustrated here. We started this work in around 2007, and of course the space industry has been informed and interested over the years, and we made an artistic impression when we went to ESA once. And we just recently got a grant from the Swedish National Space Agency to work on these materials for introducing them in satellites, and we're thinking about having these composites to replace the composites that are usually used in these solar substrates, solar cell substrates that carry the solar cells, and perhaps also in the casing of the satellite itself. But basically then by invoking an energy storing capability that we can get rid of some of the batteries. I don't know. I wasn't aware of this when I started this work many years ago, that there has so much batteries on the satellites. I understand for regular satellites you usually bring on about 250 kilograms of batteries just to power the different operations of the satellite, and particularly during an eclipse. So that's the idea, and I think that most of you know something about composite materials. You have paddle a canoe, or you've been skiing on skis or snowboards and so on. What we usually have is that we have a carbon fiber that is reinforcing a polymer, epoxy or some sort, and that gives a load-carrying composite material. Here we use carbon fibers again, but we use the graphitic structure of those fibers to allow for lithium atom coordination with the carbon atoms to actually work as a negative electrode of a lithium ion battery. So we have carbon fibers in one direction, all spread here in this direction, and then we take out electrons with the current collector at some position. We stack this on the positive electrode, ideally, and we are working on that, is to have a carbon fiber reinforced positive electrode. And we separate these two, of course, not to get in contact, and we soak it all in some kind of structured electrolyte, an electrolyte that can allow for lithium ion transportation and mechanical load transfer. And voila, we have a structured battery. And this idea came, of course, around when we were looking into battery architectures and composite materials architectures, and saw similarities both in material choice and in architecture and geometries. And we work very closely with the team at KTH, and we show in the end the entire team. But this is, of course, an effort that takes many different competencies, not only material scientists or physicists or mechanical engineers. We need to have electrochemists and polymer synthesis people and so on the team as well. just to show what we recently achieved, we had a massive response to a press release that came out a month ago. We presented an achievement in a combined material performance of a structural battery that has not been seen before. So our competitors looking into making batteries that can carry some load have either produced decent batteries. Remember that for a traditional lithium-ion battery, for lithium-iron phosphate battery, you have about 100 to 120 watt-hours per kilogram in energy density. And they reach maybe 1/3 of that, or 1/4 of that. But they came with very low modulus, same modulus as for a polymer. And every attempt that has tried to achieve higher modulus have actually failed. But we are able to make a structural battery that has these properties. And with the money we get from, and the support we get from the Swedish National Space Agency, we believe in 2 years we will be able to boost this to 75 gigapascals, which is stiffer than aluminum, and to 75 watt-hours per kilogram, which is about 60% of the energy density of that lithium-ion battery. So that's what we are aiming for, and this is where we stand just today. To do this, of course, we perform research in many different areas. And I want to just give you a flare of the work we're doing. And this is illustrating work on the device level for modeling in particular, and the electrodes that needs to be developed. You also need to have structural polymer electrolytes, and these are the ones that are developed with KTH. You need to understand how the properties between the interfaces and also the constituent materials work and so on. And we need to demonstrate that and bring it up in scale in some way. And we need to understand the performance. It's a nightmare. Every time you go to an industry, they ask for a business case. And of course, it's very different if you make a structural battery, which is to be in a jacket for a firefighter. It can be a flexible battery. So it's basically a cloth, an impregnated cloth. Then you can have very low demands on mechanical properties and can have very high energy store. But if you want to have a wing spar to an aircraft, then of course you need to have high mechanical properties, and as a consequence, less energy can be stored because of the more difficult mobility of ions. So we have all these aspects, and we need to be able to say something about the uses phase as well. And if we look at the modeling that is needed, we need to move into more multi-physics models. And traditionally, a composite mechanics person is down here and also working with thermal analysis. But here we also need to include the mass and charge balance, or as ions move and as they coordinate, we have this redox reactions taking place. And this is something that we have been working on, and we published a few papers. I will show some examples. So this is showing a structural battery with a negative electrode, the pure carbon fibers, versus a positive electrode where the carbon fibers are acting as electron conductors and reinforcements, but they're coated with the lithium iron phosphate coating, which is acting as active material then. And then we have the ions move between here. And as we charge the battery, then ions move and lithium atoms enter the carbon fibers. And then we get the swelling. And from this swelling, we actually get the change in internal stresses, because remember, all this area around the fibers is partly solid. So here we get issues about the strength of materials. And this is a link. And if we pull this, for instance, then the potential will change, because these are intrinsically coupled processes. And I want to show this video that is a paper we submitted just Friday, where we have looked at the carbon fiber negative electrode. You can see here a few thousand fibers in this very thin electrode. So it's only about 4 fibers in thickness in a stack. And these are connected and put some silver paint on. And we start to charge this. You can see that actually you get a color change for different states of charge, but you also get a contraction expansion of the fiber yarn as we get this fully charged. And as we get this charge, it shrinks back and it actually moves like this. And this is, of course, very important to understand if you want to design these type of materials, because you will get the change in internal stress state. And this has been quite neatly used also by colleagues at KTH, where they have made an actuator where you can, just by putting 3.5 volts on, you can make this 100 gigapascal stiff composite to really bend over. So it's a super cool actuator functionality coming also with this technology. Another issue that we have, remember this slide I showed here where we had the the concentrations and the change in volume. Interestingly, we also have a change in modulus. If we look at a compression test, we will test individual fibers. We can see that the transverse, the modulus in the radial direction is doubled as we dissect the fiber. So imagine that this increases about 10% in cross-section area, and it doubles its modulus. That actually will be having a tremendous influence on the stress state. And this is important to know. And now we can feed this into our multiphysics models and do a better job. The polymer electrolyte I talked about that was developed at KTH by Mats Johansson's team is what we see here. This is actually, if you look at it in a macroscopic view, it's actually a transparent film. So these voids which are containing, the channels here containing the liquid electrolyte, those are sub-micron, and they are actually not interfering with light, so they're below 340 nanometers in dimension. So this polymer backbone that we see in blue, green, yellow, red here is actually generated by having monomers in a liquid electrolyte solution. And we have some lithium salt there. And heating this solution up, we get a polymerization in the solution, and we get a phase separation, generating different types of geometries, topologies of the structural battery electrolyte. Some of these are quite soft when it comes to stiffness, as we see on this axis, whereas others are much stiffer. And some of these are actually allowing good ion transport, whereas others don't. But here we have a possibility to move up in this right-hand corner. If we had a homogeneous polymer electrolyte, we will be moving more like this. So this is a breakthrough development at KTH that allows us to make these laminated batteries at sizes about 2 decimeters by 2 decimeters. So we can make quite large battery cells now. And if you want to make them larger, we can do that, but then we need to have a denser net of collectors taking out electrons. Otherwise, we resistively heat our composite. The structure positive electrode was not used in that device I showed with the 25 properties, but we haven't since developed. So Johanna and the team at Chalmers here together with Vincenzo Palermo, an expert in graphene, have worked on a new carbon fiber electrode where we coat the carbon fibers with exfoliated graphene oxide flakes as a building scaffold for these iron phosphate particles. And we also have carbon black there for conductivity. So we take out the electrons on the carbon fiber and we take mechanical loads on the carbon fiber. So we just published this paper where we have been able to get a sufficient amount of loading on there to get properties. This is a quite busy picture, but I want to just tell you that we have energy densities for the structural electrode, which is on par with what we expect for a commercially available electrode. So that means that we can actually put this in and work as a structural battery electrode with quite reasonable mechanical properties. The volume fractions of fibers must be lower than in the other one because we need to have access to the fibers. So we just now starting to study this within a structural battery electrolyte setup. And that's the part of this Swedish National Space Agency program. We also have demonstrated this, and this is an intriguing problem then obviously. And you can see here that we have a material which is maybe conspicuously similar to something you have seen recently. It's now flying on Mars. It's our colleagues at the Oxygen company who provides the Textream technology. So we use basically their spread toes to make these single carbon fiber electrodes with unit fibers. But we have in this case also used this material to put in our 3-cell devices into a structural battery demonstrator, a multi-cell demonstrator. So here, of course, we have a pouch bag here, which is not going to be later on, but we didn't want to risk anything in this case. When we make this in the glove box, we would have had to laminate them into the glass fiber composite shell before taking it out from the glove box. And we simply didn't want to bring in the epoxy in the glove box at this stage. So that's why we did it like this. Then we laminated up with the Textream, the cross-ply laminate that we saw the woven material that is flying on Mars as we speak. And this is causing some issues actually, because when we make our cells, we are not having access to any automated method to do this. So actually we make cells with a greater variety in properties than you would have if you buy a laptop, for instance. So we get differences in impedances, and the resistance of the system is actually affected by the variation in cells. We have since teamed up with colleagues at electrical engineering to get help with battery management and stuff like that. But this is working and is demonstrated. So we work now quite a lot. We have a big bucket filled with lots of energy, but the hole we have drilled to empty the energy is too small, so we need to increase the power. To do that, we use ultra-thin separators. We work with people in Michigan, University of Michigan and around to find ways to reduce this distance to only a few micrometers. Also, we need to characterize the multifunction performance in concert, doing the mechanical and electrochemical test at the same time. We have seen if we load these that actually we get quite good properties. The mechanical properties when it comes to stiffness is maintained, whereas the strength is reduced by 25%, but regained as we discharged. So that's actually something that is important to know, that we can use these in concert and get out the mechanical properties even though we have full charge in the battery. But this we need to work on much further and to see what limitations there actually exist. And also we need to work on structural barriers and more efficient collector solutions. We also need to make sure that we have a good verified version of the structural positive electrode that can be used in the structural battery. Just to round off, I want to show the entire team. So here you have the Chalmers colleagues from electrical engineering and then applied mechanics and physics. And then we have also the electrochemist and the polymer synthesist and the materials mechanics person at KTH and the entire team. So I hope I have time for one or two questions. And I'll stop there. Thank you.
Thank you, Leif. Yes, there is time for questions. I haven't gotten the questions through yet, but I'll ask you a question myself first. What is the kind of time scale that we can expect this to be on a satellite, for example, since we are talking space?
Yeah. So this is, of course, a very important question. So this is done in the lab at the moment. Mm-hmm. So we have reached TRL4, you can say. We know that lithium-ion batteries can be in space and work, so that should be, since we have the same chemistry, that should not be an issue. But of course, there is work to do to upscale this. It's work to do to get these consistent properties and performances of these battery cells one by one. They should be identical. There is a need to increase power, so we now can charge full and really fill our entire available capacity of the battery in 10 hours. We would like to do it maybe in 1 hour. So for this, we need to get these more efficient power solutions in place. So I think that this can be suitable and could be picked up by industry and be in a laptop in 2-3 years or 5 years for sure. For space, I'm less sure. Also regulations, certification, procedures is something that needs to be handled. Here I know if I go to Airbus, they have one wall filled with documents for the structures and also another wall for the electronics of the aircraft. And here we're going to bring some new stuff to the table, which is lacking standards completely. So I think it's a way away still.
I was also wondering about the harsh conditions that the material would be exposed to. If this could possibly be break our enthusiasm here. I don't know.
For a composite material performance, this flying lab is on March today, and also the lithium-ion batteries are also in all these devices. And we have traditional composite materials, but we have the traditional polymers that we use in this SPE, the liquid electrolytes and the redox reactions taking place in this structured battery are the same as the ones that are flying in any satellite today. So for that reason, I don't believe that we should expect problems of that sort. But there are, of course, maybe complications. Maybe you need to keep it warm or at a certain temperature if you want to have it in those solar panels. Maybe you need to have a heating device to make them keep them at the right temperature and so on. These are issues that we are open questions actually.
I got one quick question still that we can take. How do structural composites react to impact?
So of course, then that's the Achilles heel of any laminated composite. That the impact load out of the plane will cause delaminations. Delaminations here will cause most likely short circuit or loss of electrochemical functionality, as with a reduced compressive strength of the structure. So of course this is critical, and one has to compartmentalize cells here, I think, to allow some cells to go bust. So, but this is of course, there's no way to repair in space in that case.
No. I got another question. Are the rotor blades of Ingenuity also batteries?
No, but they're made with the same spread toe technique. So, you know, if you buy composites today on the market, the thinnest one that is flying in an aircraft is 128 micrometers in thickness, and they stack a laminate from that. What they do at Oxygen is providing 20 micrometer thick. So these super stiff and strong wings that we see on that rotorcraft are very, very thin.
No.
Much thinner than anything flying in an aircraft.
Okay, thank you. And with that, we will go to our next talk, for which I can introduce you to someone who's worked for over 25 years at NASA, starting off, as he puts it himself, as a Jedi, and now being somewhat of a Yoda to his own students. That man is Larry Toops. Those are his words, not mine. This is Larry Toops, NASA Emeritus at Johnson Space Center, where he's been responsible, or still is responsible, for work related to future habitat concepts for future missions beyond low Earth orbit, such as the Moon and Mars. He's also adjunct professor in the Space Architecture program at the University of Houston, and is adjunct in the Architecture and Civil Engineering School here at Chalmers. So, Larry, how do we pioneer an extended human presence on Mars that is Earth independent? Please tell us.
Such an excellent question. So, again, thank you for the invitation to share a short story with you here. I have a few minutes to communicate it, but what I wanted to weave in the story is that while we see all these wonderful technologies being developed, all the excitement about exploring space, that the message I'd like you to take away from today is that we can plan for that future, but by looking at the past. If you look at this picture here, we hear conversations about humans traveling to Mars. This is a vision by SpaceX of a sustainable Mars base, and it illustrates a robust and sustainable settlement. It includes things such as domed habitats, greenhouses, roads. But to step back from this, you have to remember that certainly the first missions that we'll conduct with humans to Mars prior to this vision will focus on getting just a few people safely to the surface and then back to Earth. But over time, if our real vision and our objective is to stay there for extended periods of time, I mean, how do we pioneer an extended human presence on the Mars surface that is truly Earth independent? For over 20 years, we've had a continuous human presence in low Earth orbit aboard the International Space Station. This is an incredible feat of engineering, and it's been sustained mainly by its proximity to the Earth. Station is approximately 420 kilometers above the surface of the Earth. And because we've had a robust transportation system of resupply from Earth, we've been able to enable timely delivery of both crew, as well as the logistics that are needed for resupply and sustainable operations. However, if you look to the future, long duration missions that will last up to 3 years to, say, Mars, will require us to develop a strategy that enables independence from Earth and also lessens the reliance on Earth for that resupply. It will mainly focus on logistics and consumables being provided by the destination itself, in this case, Mars. So what I'll share with you here for a few minutes is some work I was involved in back in 2013 It was called the Evolvable Mars Campaign. It was a study that we did at NASA. And we developed an approach, a strategy that I think is sort of a backbone for my story here, okay? The initial phase is called emplacement. Mainly this is where we enable the landing of the first crews to the surface to establish a human presence there, at least for a short period of time. But over time, after adding additional surface assets, such as larger living spaces, rovers for mobility, and more robust power systems, we come to a point where we've accomplished what we called our first threshold goal. And that was to enable an Earth independence for a certain period of time, 12 to 18 months, for 4 to 6 people. The second phase, which we called Mars Surface Proving Ground, is a period of time where the buildup of capabilities takes place and technologies are demonstrated and proven at that initial emplacement location. But by doing these demonstrations and developing these technologies in place at Mars, we will learn truly how to be Earth independent. And so a second threshold goal or ultimate goal enabled is where at the end of, quote, this phase, you're able to enable an indefinite stay and create less of a dependence, if not total independence from Earth. So the third phase, which is illustrated on the lower right, is called utilization. This is where 4 people will be staying on the surface of Mars, maybe a few more, but with an indefinite stay time and with minimal and hopefully ideally zero resupply from Earth. Now keep in mind when you look at this, this is not really a timeline, but it does allow you to strategize about things and also identifies some major milestones, which once they are achieved, you can conduct yourself and progress on to the next phase. And again, the ultimate goal here is that Earth independence on the surface of Mars. So looking at it a little bit more in detail, this evolvable architectural approach, particularly going by phase, is that during emplacement, right, you'd have basic habitation modules built on Earth, delivered and sent to Mars that would be provided. The operations you're conducting there by the crew would include the use of mobility devices such as rovers and robotic assistants. The extensive Mars Surface Proving Ground phase would see more detailed science investigations and demonstrating technology concepts that respond to the constraints imposed by the Mars environment on the people and the hardware. You're looking at developing things in place in the relative environment. And then once you get to what is again called utilization, that's where you make routine use of the local resources that are there. And by doing that, you can produce building materials and life support system consumables. So during this Mars Surface Proving Ground, the area that I've been most interested within my career at NASA and post-NASA in my teaching is in the area of habitats. So if you look at sort of a more detailed list of some of those tests of technologies and operations that relate more towards the habitation part, you know, it would include looking at more mature and sustainable habitat designs, looking at things such as inflatables, use of in situ resources to create the habitats themselves, a closure of life support systems, again, utilizing local resources and not consumables that are brought with you, the idea of an extravehicular or spacewalking test bed to learn and effectively do EVAs in a gravity environment, and also ergonomics research, learning how the human body reacts to the reduced gravity on Mars and how that might affect interior layouts for the habitats and the laboratories you'd be providing. What I'd like to do now is just take a minute or two to sort of relate to you sort of what came out of our Evolvable Mars campaign. We came up with this concept called an exploration zone. An exploration zone is a 100-kilometer radius, approximately, with a central landing spot for the crew, where the habitats, the power systems, and the rovers that I've been describing here would be based at one location. But within this 100-kilometer zone, the science community would have science regions of interest. Those areas that hold clues to, say, life on Mars, as well as some of the other science questions that the community at large has. But that exploration zone would also have what we called in situ resource utilization regions of interest. And those are areas where you would have pockets of material within the soil, if not the soil itself, that you could use for building the necessary infrastructure at the central base area, again, mining it to produce consumables that you'd need. We included within this activity a workshop that we conducted back in 2016. And we had the science community and the engineering community come together. We had about 200 participants, and that collective workshop identified over 40 different potential exploration zones on Mars. So let's go ahead and get on with it here. You know, what is the mindset of being a pioneer and going to Mars? You see here, Elon Musk and SpaceX can certainly fit the mold of pioneers for space right now. Developing reusable rockets, including the massive Starship shown here at their test facility, which happens to be in southern Texas, just south of Houston here. They've truly revolutionized space exploration. But now I'd like to turn this talk in a sort of a different direction, looking at the pioneers of Antarctica, such as Ernest Shackleton and his ship Endurance in the early 1900s. The Norwegian, British, Swedish expedition, or what was referred to as NBSX, was conducted from 1949 to 1952. The significance of it was that it was the first Antarctic expedition involving an international team of scientists. It was led by John Giovera, a Norwegian author and polar researcher, but the team was composed of members from Norway, Sweden, and the British Commonwealth of Nations. The expedition established a base camp known as Modheim on the ice shelf along the coast of Queen Maud Land in February 1950, and it literally mapped 60,000 square kilometers by ground survey. And as you can see within this picture here, this is the expedition composed of 15 crew members. They were transported aboard a 600-ton sealer named Norsel. That was their starship of the time. And as you can see by these pictures, it shows that not only dogs as well as tracked vehicles were used to carry the necessary logistics such as food and consumables. Again, no use of local materials, particularly at that very early pioneering stage. If you step back for a second and look at NBSX and compare it to a Mars mission, they both involved about a 3-year durational stay at their location. And as you can see, they sort of mirror each other in terms of a fast transit there with a long stay at the destination. So what did we learn from some of this? Pioneers such as Shackleton, the NSBX expedition, and subsequent exploration of Antarctica was that the concept of what's referred to as a field station was useful in dealing with unknowns. Unknowns are those scientific investigations to understand and answer questions about a new environment to humans, in this case, Antarctica, but of course in the future of Mars. Field stations bring the basic tools of research to the places that they are needed. That includes electricity, communication, but at the same time, they create a bridge between the natural environment where we're able to send maybe just a few people initially and the research laboratories distributed on Earth for those that are unable to be there. You can see in this picture here, this is McMurdo Station, the US station in Antarctica. But if you look at other stations, such as the Swedish Wasa station, it's just one of 70 permanent research stations scattered across the continent of Antarctica, which represents 29 countries from every continent on Earth. And as you see here, some more representative stations everywhere from Australia to Russian, but they're all located in a neutral region of Earth where scientific research is the primary driver. And they're characterized by small scale structures providing shelter and necessary sort of resources in place. So let's revisit the Earth independent strategy that we looked at for Mars, and then overlay the evolution of a place, say, such as McMurdo Station. 1902, the explorer Robert Scott in 1902 established what's been called now Scott's Hut. It's on the edge of the ice shelf of Ross Island. It established a small structure for shelter and storing logistics, particularly on Scott's journey to the South Pole. Fast forward to 1955, with a full year permanent occupation, the first year of that at McMurdo, became basically a collection of various structures and infrastructure. Then seeing McMurdo today, it's Antarctica's largest community. It's capable of supporting up to 1,200 people in an extreme environment. The timeline here illustrates, in my estimation, that going from an initial foothold to permanent occupancy took well over 100 years. It evolved over time and was dependent on the funding and the effort, obviously, put into that initiative. But my proposal, my thesis here, is that Mars will be the same, maybe not in total time, but again, it will depend on funding and initiative and a period of time that will take place to go from emplacement to utilization. So what have I proposed to you today? Okay, that we can look back at pioneers of the last discovered place on Earth and learn from them how to pioneer a planet that we've yet to set foot on. Consider that initial exploration of Antarctica was done by humans. This Mars exploration family portrait illustrates that the initial exploration of Mars has been well underway for over 20 years by robotic pioneers. You can see multiple nations here that have sent numerous rovers and orbiters discovering and documenting the topography and environment of Mars. And as Leif just mentioned, we have our newest Mars pioneers that have just arrived as of February of 2021. Perseverance to join Curiosity, and Ingenuity, which Leif described briefly within his talk, had a successful completion of the first powered controlled flight by an aircraft on a planet besides Earth, taking off vertically, hovering, and landing. But definitely these robotic pioneers are using the Mars surface proving ground that is there as described earlier. So to sort of conclude with this, I firmly believe exploration is in the human spirit. And whether it's Antarctica or Mars, the pioneers, whether they be human or robotic, enable a future we have just started to envision. Tack så mycket. Thank you.
Thank you very much, Larry. That was a very interesting vision of the future. I got a first question here from our audience, and that is, how can we make sure the human presence on Mars is sustainable, let's say ecologically, in the long term?
That's a very important question, and it's a complicated one, of course. I think in terms of enabling a sustained human presence there, we will have to use the local resources that are provided there in a very wise way. Things such as growing plants, actually producing the propellant that's needed on a return mission from the surface of Mars. You'll see in Rob's talk, but it's totally necessary that those be produced locally. Budgets and just the engineering challenge of it all will not allow us to bring everything we need to Mars for a sustained visit. I feel like by going to Mars, similar to Apollo, we will learn and uncover technologies that we really, at the moment, maybe don't even have a clue what they might be, that will enable that sustainability, cleaner water, revitalization of air, and also making so that the crew themselves become more, what do we call, they're autonomous. They will be on their own. They will not be directed by a mission control at Earth.
I had another question myself. You mentioned Antarctica because this is indeed a very important testing ground, one could call it. So McMurdo Station supports 1,200 people, you said. How
Yes.
self-sustained are they? I mean, how independent of, well, not Earth independent, but how independent of the rest of Earth are they?
Well, you know, it depends on what season of McMurdo you're in. Overall, McMurdo and a lot of the Antarctic exploration learned lessons that having non-sustainable, very dirty power systems such as diesel are not the way to go. So things have evolved from that going forward. Now, getting back to your question, how sustainable is McMurdo? During the summer season at McMurdo, it blossoms to that 1,200 people. There's one mission per year going to McMurdo from Christchurch, New Zealand, that delivers consumables and takes away recyclables and things that are going to be recycled back in New Zealand. But during the winter season, that 1,200 goes way down, probably maybe even a tenth of that population. And during that winter season of McMurdo, that particular smaller group are more sustainable than that larger group, because by that part of the season, what's been delivered is in not short supply, but in less supply. They actually have a greenhouse there that they utilize for growing plants, but they do get very sensitive about not wasting items, and nothing is trash or waste. It's a resource that they use there.
That sounds like a good plan. Thank you, Larry. For our next talk, which is the last one of the day, we will continue along the lines of Earth independence, and we will link it directly back to the actual production and the usage of material in situ. So whether you're on the lunar surface or on the Martian surface. And for that, I am pleased to introduce Robert Mueller, who is a NASA senior technologist for advanced products development at NASA's Kennedy Space Center in Florida. He's also co-founder of the NASA Swamp Works Innovation Labs and the Kennedy Granular Mechanics and Regolith Operations Lab. He's also Kennedy's lead for autonomous robotic systems involved with in situ resource utilization. That was a long list of things. So Robert, we will switch to you and listen to what we can do with regolith and other materials for Earth-independent production. Please.
Hello, it's a pleasure to be here. Can you see my screen?
Yes, we can.
Okay, what I'd like to do is follow up with Larry's talk and dive into the details a little bit more. Larry gave a great vision of what we intend to do to expand humanity into the solar system. And so now I'm going to tell you about the very next steps in that journey. And that journey started in the 1950s with a Mercury program. On the far left, you see the logo, the Mercury 7 is what they call those astronauts. And then it moved on to the Gemini program. Of course, Apollo, everybody knows, we landed on the moon in Apollo, very successful campaign. And then Skylab was an orbiting station, arguably the first US space station. And then Space Shuttle was developed, which was essentially a large cargo transportation vehicle. And that helped us build the International Space Station, which, as Larry said, has been flying for 20 years with a permanently occupied human presence. It's quite an achievement. And the next step is the Artemis program. So the Artemis program is also divided into phases, and the Artemis program will go to the moon. And even though the Mars is the ultimate goal in NASA's plan for human presence on Mars, Mars is a long distance away from Earth. It takes 6 months to travel to Mars. Once you're there, you're committed to 1.5 years of staying on the surface, and then you have a 6-month journey home. So it's a 2.5-year commitment, very dangerous. So it makes sense to use the moon as a proving ground. The moon is only 3 days travel away. If you have an emergency, you can come home. Even if you run out of food, you could probably come home and survive the 3 days. So this is a good reason for going to the moon. It's an extreme environment. It has a lot of resources, and we have an official policy in the United States to be at the lunar South Pole by 2024. Of course, it's not just the US by itself. There is a group called the International Space Exploration Coordination Group, ISEG, and this is the plan that came from their report. Now, I did notice Sweden is not a member of this group, so that's something you might want to pursue. And this group meets on a regular basis, and they put all the missions on the table, and they try to maximize the investment of those missions so we can all help each other. And this is what this roadmap is showing. It's showing all the different missions and how they interact with each other. So in the gray bar there, you'll see in the next few years, it's going to get very exciting. We're going to have probably one lander every 6 months landing on the moon, doing the necessary preliminary steps to find out how is the local environment in this region where we intend to land. And then you see the first human landing system in the 2024 timeframe. And then we'll land humans on the moon every year. So this is going to get very exciting. And we're also building up the infrastructure as we go along, because as you build up infrastructure, it becomes more sustainable. You can't have sustainability without some infrastructure. Once we've achieved what we call boots on the surface, and we have the initial transportation capability, in phase 2, we'll look at the proving ground aspects, the Mars forward capabilities, and a sustainable lunar presence. So most of NASA, I would say 90% of NASA works on the transportation, how to get to the moon. And it's important. But there's a small group that's growing, maybe 10% of NASA, and I'm a part of that group. We worry about what do you do when you get there? And this is called the surface systems. We have a program called the Lunar Surface Innovation Initiative, and is divided into these main categories. And these are the technologies that NASA is investing in order to make this lunar surface a sustainable endeavor. And specifically, I'm working in the area of in situ resource utilization, which is living off the land on the Moon and Mars, using local resources to be sustainable. And I'm also working on surface excavation and construction. Those are my two areas of expertise. NASA does have a heavy investment in advanced manufacturing technology. And I really like this expression: manufacturing drives innovation, and innovation drives manufacturing. You'll see that the countries that have lost their manufacturing capability have started to decline in innovation as well, because you can't throw it over the fence and just say, go manufacture this on the other side of the world. Your engineering capability and your innovation capability starts to suffer. So manufacturing is a very important part of innovation. At NASA, the top 5 drivers are listed there, and the top 5 technologies we're interested in are listed below that. You can see that additive manufacturing is an emerging discipline of tremendous importance, and you've already seen that in the other talks today. Now let's get to the really important matters here. What do we have in space to survive? Space is a desolate place. It's hard to survive in space, but it's also full of resources. Every element in the periodic table is out there in space, and the Earth is made of all the materials that are in space in abundance. So if we look at it that way, if we change our lens, our perspective on what is out there in space, we actually start to realize that it's an incredibly rich place. It's rich in natural resources. And when you look at the resources at each destination, we have 3 major destinations: Moon, Mars, and asteroids. On the Moon, we have a lot of silicates, and silicates contain oxygen. 42% of the regolith on the Moon is oxygen. If we can extract the oxygen from the regolith, we have breathing air. We also have rocket propulsion oxidizer, which when you combine it with fuel gives you the propulsion system. Hydrogen and oxygen is the most efficient chemical propulsion system that we know of today in terms of high thrust propulsion. And the space shuttle used hydrogen and oxygen. So this is a very good resource to have. And we also have other minerals in the lunar regolith. And I'll talk about the regolith in a minute. The regolith is the crushed rock on the surface of the Moon. And if you take that crushed rock, you can extract oxygen. You can also extract metals. And recently, we've discovered water on the Moon. In the Apollo days, everybody thought there was no water. But the Apollo missions went to the equatorial regions, and we found the water is at the poles. That's why NASA's going to the lunar South Pole. That's where the water is. One of our main objectives is to find the water so we can use it as a resource for propulsion and survival. On Mars, we have a carbon dioxide atmosphere, 95.5%, and it's a little bit friendlier than the Moon is in terms of an environment. And then asteroids, of course, they have a lot of materials on the asteroids that are very useful, but they're mostly in the asteroid belt, which is beyond Mars, so it's a challenge on getting there. Now let's dive into the rock. One of the most common rock substances available on the Moon is called basalt. And basalt is an igneous rock, and it essentially is lava that's cooled down, and it forms this basalt material. And you can see the chemical composition. It's half of it is a silicate, silicon oxide. And so this is where the oxygen can come from. But it also has a lot of iron in it, a lot of aluminum in it, a lot of magnesium, and titanium as well. So these are very useful materials. If we can extract them from the rock, then we can certainly use them. But if you don't have the technology to extract it from the rock, it's still a useful material because it's a very strong material. It's a structurally strong material. If you compare it to concrete on Earth, the Portland cement concrete is about 20 to 40 megapascals. but basalt rock is 62 to 103 megapascals in compression. Recently, we've taken the crushed rock and we've turned the crushed rock back into solid rock. And we've found that the compressive strength of a sintered Hawaiian basalt rock is 206 to 220 megapascals. So if you look at these materials, purely from a materials point of view, we have a material on the moon that's readily available that can be processed, and it will be 6 times stronger in compression than normal Portland cement concrete typically used on Earth. So how can we use this rock? Well, this is nothing new. Over the last 2 centuries, we have been using rock. And in fact, if you look at all the structures that have survived over the last 2 centuries, these are the cathedrals, the amphitheaters, all these magnificent structures, even the roads, Roman roads still exist today. And these roads and structures were mainly built out of basalt rock material. And so we have a very good history here that shows us that this material can survive. Now, if you look at the surface of the moon, it's covered by regolith. It's 10 to 20 meters of regolith across the whole surface of the moon. And what is regolith? Well, it's basically crushed rock, but it's very, very finely crushed rock. It's been bombarded, it's been hit. The moon has been hit by high energy impacts from meteorites, comets, other objects, and it's pulverized the rock into a powder, a very fine powder. It's between 20 and 100 microns. 80% of it is in that size range. Some particles are bigger, some are smaller, but in general, it's a very fine powder. Think of it like talcum powder, but it's made of crushed glass. Each particle, if you look at that picture in the middle, each particle is not smooth and round like beach sand. This is a very complicated morphology. So the shape of it is called the morphology, and that's a very complicated shape, which gives it unique properties. Now, the good news is this is a feedstock. If you have crushed rock, this is something that's a resource for construction. We actually spend about 6 to 7% of the world's energy to crush rock for construction. So this is a lot of energy that we've saved because Mother Nature has crushed the rock for us. And so this rock is readily available. All you need to do is scoop it up. If you scoop it up, now you can do something with it. You can bind it. There are many ways of binding it. One of the most promising areas is called sintering. When you have thermal sintering, in the picture on the top right, picture A is all the little particles. If you heat up those small particles of crushed rock, the outside surface starts to melt. The whole particle doesn't melt, but the outside surface starts to melt. When this outside surface starts to melt, the 2 particles are stuck together by the melting rock fusing together. And then this is what we call sintering. If you bring the temperature to about 1000 degrees Celsius, you can sinter this rock and you can create a structure out of it. And that's what's shown on the right is a regolith simulant that's been sintered in an oven, and it's created these test materials. Another thing we've done is we have actually taken the regolith and we've used a laser to 3D print with it. So we've been able to 3D print these small cones, and this is just a proof of concept, but it does show that laser 3D printing with regolith is feasible. Now, why do we need these materials? Well, we need shelter. We need shelter from the exhaust plume from the rocket engines. We need shelter from the radiation, which is coming in from outer space all the time. We need shelter from micrometeoroids, which are still coming in today. We need shelter from the thermal environment, which is an extreme thermal swing from about minus 170 C to about plus 130 C, depending on where you are on the moon. So this is why we need these materials. And what would we do? What are the construction tasks that we would do? Well, you see a long list here. Starts with launch and landing pads, and then we need lighting systems, blast protection berms, roads, we need power systems. And so we need foundations, we need structure, we need buildings, we need unpressurized structures, we need pressurized structures, we need dust-free zones, we need energy storage zones, and we need to acquire propellant and store it. So there's a lot of infrastructure that's needed. In the very early stages of this infrastructure, we're still learning how to do it, and we're developing the technologies. So NASA believes in tapping into the public intelligence, the open sourcing of intelligence, and bringing in the crowdsourcing for new ideas. So we had a competition called the 3D Printed Habitat Challenge. In that challenge, we asked the competitors to use a regolith-based material to 3D print a structure. This is a regolith mixed with a recyclable thermoplastic polymer. So think of the drinking bottles you have. If you melt those down and mix them with a regolith in a ratio of 70% regolith to 30% polymer binder, you can actually create quite a good construction material, and you can extrude it out in a melting process, layer by layer, to build very nice structures. And the winner here was Branch Technology. This is a small startup architectural company, and they managed to win phase 2. In phase 3, we had an on-site competition where everything was scaled up. And now we wanted to see a 1-to-3 scale structure of a Mars habitat. On the left, you see Pennsylvania State University. They're using a geopolymer concrete to 3D print a structure that you see with the 2 domes there. On the right is AI Space Factory, and they're using the thermoplastic polymer binder with the regolith to 3D print another structure. In the end, the structure on the right was the winner, which was AI Space Factory. And the other one lost, not because it was necessarily worse, but because the rules were set up for automation. And 3D printing with the slurry was much more labor intensive and was not as good for automation. So they had a lot of interventions, human intervention, and that reduced their score. So that's why they didn't win. But in the end, the AI Space Factory team won, and this is their vision of habitats on Mars. And you can see that these structures could be 3D printed. And in fact, this company is commercially continuing and building these structures on Earth as well using recycled plastics. So in conclusion, if you think we have a resource challenge on Earth, that's simply not true. We have a whole solar system and a universe beyond that solar system filled with unimaginable resources, this vast, vast abundance of resources. All we have to do is have the imagination to go and harness those resources and turn them into something useful. So that's the thought I'd like to leave you with.
Thank you very much, Rob. I think that is a very nice message to end with. I hope everyone will be inspired by this. I will check whether I got any questions. Not yet. So I have a few questions myself. I mean, this is very inspiring stuff. There must be so many questions. So when you talk about the extraction of different minerals or oxygen and hydrogen from the rocks, how efficient is this? And I mean, are the processes that we have realistic for a very soon to be established kind of workable solution on the moon?
The key to exploration is energy. If you have energy, then you can do all kinds of things and extract the metals, the oxygen, all the resources. You can mine the water ice, turn that into drinking water. You can make propellant from it. You can have fuel cells. So you need the energy. Once you have the energy, in terms of efficiency, which is what the question was, NASA is currently focusing on 3 types of ways of extracting oxygen out of the regolith, and they're all chemical processes. So the first one is hydrogen reduction. This is when you take the regolith and you heat it up with a hydrogen gas. The hydrogen reacts with the iron oxide in the minerals, and then we can extract the oxygen in the form of water, and then we electrolyze the water to have the hydrogen and oxygen. You can run the hydrogen back through the system, and it keeps going. So that efficiency is 1%. You can get out 1% of the material. And then the second one is the carbothermal process. This uses the Sabatier process, where you put methane in instead of hydrogen, and the efficiency of that is about 12%. But then the ultimate goal is to use molten regolith electrolysis, where you take the rock and you melt it. So you turn the crushed rock into lava, and then you put the electrodes, the anode and the cathode, into the lava, and you put a current on it. On one electrode, you get the oxygen, and on the other electrode, you get the metals. So this efficiency is 28% of oxygen extraction, and you also get metals as a byproduct. And so this is the preferred approach, but it does require a lot of energy to melt the regolith. It's similar to making aluminum. So these are the trade-offs we have. But currently we're looking at all different processes, and the leading ones, of course, are if we mine water, we can simply melt the water ice and electrolyze it. And if we get the minerals at the south pole of the moon, they are less rich in iron oxide. They're more rich in a mineral called anorthosite. And in that case, the carbothermal process is the best process to use, which has a 12% efficiency.
Okay, thank you. I got a question. Could the Mars dust be compared to the moon regolith and be used in the same way?
Yes and no. Mineralogically, there is a lot of basalt on Mars. It's an igneous planet. There's a lot of volcanic activity. So in terms of basalt, yes, Mars is similar to the moon. But in terms of particle shape, it's different. Mars has had a weathering process. It's had wind and water in the past, which has changed the erosion properties of the granular material that comes from the rock. So the regolith properties, the geotechnical properties, are very different on Mars than they are on the moon, and there's a small atmosphere. The atmosphere is about 1% of the Earth's atmosphere in terms of pressure. But it is an atmosphere, and that's why the small helicopter was able to fly. It's a very small atmosphere, but it's there. On the moon, we have no atmosphere. It's a vacuum, and these particles haven't been touched by any kind of erosion, so they're very sharp and angular. So it's a very different geotechnical aspect. So in some ways it's the same, in some ways it's different, but the moon is different than Mars.
It almost sounds like you're saying that it would be easier to work with the Mars dust than with the lunar dust. Is that true, or did I misunderstand?
It's less, the Mars dust is less abrasive than the lunar dust. So in that situation, it would be better. But there are toxic chemicals in the Mars dust that we found, hydrogen peroxide, that are toxic to humans. So we have to worry about that too. Okay. So this is still a area of research. There are advantages and disadvantages to both. One of the good things about having sharp angular particles is the angle of repose is very high, which makes it a very good construction material.
Okay, thank you. I got one last question. Thermoplastic/thermoset polymers come with lots of challenges, such as structural integrity at elevated temperatures. How do you look at it, and will it be challenging in an actual application?
Yes, it's true. Thermoplastics have creep at elevated temperatures. If you put a load on a plastic, then the material starts to creep, and that could be bad for a structural application. But the way we handle that is we have so much regolith available, so much material on the surface, we can make a structure with a thermoplastic concrete, which is regolith mixed with a thermoplastic, and then we can cover it with regolith. We need to cover it with a shield anyway to shield from the radiation and the micrometeorites. If we can cover the structure with a regolith, now we don't have the elevated temperatures because it's a very good thermal insulator. And we don't have, it's shielded from radiation, it's shielded from the thermal environment. So now we don't have a problem with using the thermoplastic materials.
Okay, thank you very much. And with this, we actually conclude our block on production in space. And I welcome Lars Nyborg back to the stage. Please come and join me.
Thank you.
We will try to give a sort of a summary to the afternoon. Maybe I can ask Lars what you would take away as the highlights of today.
Do everyone hear me? Yes. I think what was very interesting and a highlight, and hope everyone joins me in this type of conclusion, is this really fact that we bring quite a lot of nice contributions that brings basic sciences on the scene. We go through the engineering aspects here, and we see that there is a lot of cross-disciplinary connections that we can bring together if we just take a theme that is production in space. That's really my main home take out of this, that there is a lot of connections that we can build on, develop and create something that is novel. Another thing that I think is important is that now we talk about manufacturing, production in space or production for space, whatever it is. There's a lot of technology, there's a lot of high tech involved here. But it is also though that creating solutions, we heard last now from Rob Mueller here, about that are very harsh conditions, right? Yeah. Mm-hmm. It's not easy. It's not easy to get things done, right? Yeah. But once if you get things done on whatever solution you have there in these circumstances, we can have it, which I think it's also some home take here, where we spill over, that we can bring certain solutions that have been there, that were developed for applications in space, and we can actually bring them back to Earth. And whatever we can create under these sort of very tough conditions must be sustainable. Mm-hmm. There is no other way, because will not tick if it's not sustainable. And that means it also brings an aspect of bringing sustainable solutions back to Earth in the long run. These are two conclusions from me. I don't know if they make sense or not, right? Yeah.
I think they make very much sense. Sustainability does seem to be the key aspect that is driving much of the science and technology development and plenty of innovations that are going on. The EU Commission now also came up with a space strategy, and sustainability is the core of all that we have to do in the future, and this only makes sense, I think. And I agree that we have to, when we look at space, we're bringing together anything from basic science, whether it's then the people who actually want to look into space. Yeah. We also drive the requirements, but it's also people who do basic research on the materials that actually can be used to then bring them to space. And then if we can connect this to all the engineers that can help us build these new solutions, that can come with new sustainable solutions, and then bring this into an ecosystem where the entrepreneurs can also bring these solutions into reality. This is like the long chain that we have to link together. And I think at Chalmers we actually have a lot of these different aspects, and not everyone is connected to production in space, of course, but there is so much space to be done, and it's becoming an increasing business, as we've heard before. I think it was Anna who mentioned the booming business globally when it comes to space. We have to connect people in the right way. Space is no longer just this really strange, far away, exotic thing. It's becoming a reality for more and more of us, even if we're not aware of it always. But it is becoming a part of our day-to-day needs and necessities. So I think if we can bring together people in a good way, the researchers, the industry, and and society to set the needs, then we can actually move forward in a good way, I think. And I think production in space and for space is clearly also a very important part of this.
I hope so. But it's not just production, it's the whole space research that we're talking about.
Yes.
But we, as representative for Area Advanced Production Area Advanced, of course I feel that whatever manufacturing materials can get in place, and that we can take the potentially this could be one of our themes that we address in our coming years here, in our sort of work plans for coming years. And of course we can't promise that this is a huge investment we do from Production Area Advanced, but this at least inspired me for saying that, well, we should not forget this area. So if we should do something in coming years at Chalmers, at least what we could be controlled from our capabilities.
That sounds...
That's whatever that means, right? Yeah, so
that sounds like an excellent way forward, I think.
Yeah.
And I'm sure that actually other areas of advance will, or I hope that other areas of advance will have the same stance, because space seems to be pervading everything we do almost, which is surprising. But yes, having this broad platform at Chalmers, which we're trying to set up currently, is something that we hope will really connect the very many different perspectives within space science and technology at Chalmers here.
Yes, I like it. Being a researcher in the area of additive manufacturing, powder technologies, I heard here myself, I see a lot of interesting sort of options. And there's one thing that I'm just wondering about, and that is, if you look on what Larry Tobes talked about, and he made this historic view back, right? Yeah. Go to the poles and finding ways to fix things there. But be honest now. We are so used to the day that we can have access to all kind of materials. If you look on the sort of cultures back, where have a fantastic sort of development of mankind using Stone Age materials. So, in one sense, we can create a lot of stuff, but just using the raw materials that is there, and we're not necessarily going. The question was said, making metals, but do we need to make metals out of everything? Can't we use just the minerals as they are and bring them into synthesis, because that's the original way of making buildings, right?
I think this is where Rob's quote on imagination comes in.
Yeah.
So the resources are there. There's no lack of that. I don't think there's a lack of imagination, by far not. But it's a matter of getting people together to actually foster that kind of environment where people can just let their imagination loose on problems like this.
But look on all ancient societies. They stone buildings, big stone buildings.
Yes.
And tell me, why do they start to build pyramids in the Americas? Why did they start to build pyramids there? They built pyramids. Did they talk to one another?
I don't know.
But they created big stone or mineral-based buildings, right? Yeah.
Yes.
With advanced technologies, with the resources they had then. I mean, where is the problem?
I'm not sure what.
I'm sorry to say.
I think when it
but
comes
if you look
to
create habitats, this is what I'm meaning. Yeah, I'm actually more a material scientist, but I just wonder about. You can create a lot of stuff really if I using the dust from dust to stuff, or I don't know what it is.
That seems to be what they are trying to do,
Exactly.
right? They're trying to just use what is there. So this is a major advance.
And that's in some sense sustainable. Yeah.
Yes, hopefully. This is the ultimate goal, I think.
But Elvire, thank you very much.
Thank you.
You did excellent work here, kept everything together.
Thank you.
I
I
would
think
like to
the
thank-
most of the work was done by our excellent speakers.
Yeah,
so
and we need to thank them all
Exactly.
because they contributed fantastically to what has happened here today. And whatever questions. And remember, May 4th. Today is the real Star Wars Day.
So
That's-
May the 4th be with you, right?
Yes.
And then tomorrow is May the 5th, and I heard that there's something about going to the dark side tomorrow, because also the evil people need love. Okay, I think we can conclude on a very strange note. I hope everyone enjoyed the afternoon, was inspired by the many different talks, and if there are any further questions, people can always contact us through the channels that were made available. And with this,
we all like to direct the thanks to. There is some Karina is here. Where is Mikael?
behind you.
Here, behind me here, and with this, Mikael, to you, Elvire.
Thank you very much.
Thank you.
Thank you.
So, thanks, everyone.